Oh, thank you. Thanks. So, how are we able to control magnetism or the idea that two things can attract each other or repel each other, especially with let's say the tools that we have, that is wires, that are microcontrollers, that is voltage, currents, etc. And the important thing here is the concept of induction. Probably you know this from the kitchen, but the idea is that we use current through a wire generates a magnetic field, always. In any wire that you have, if there's current going through it, there's a magnetic field around it. And the idea we're going to use is that we're going to make a very long wire so that we are able to generate a very big magnetic field. And that brings us to the concept of coil. Coil is this. Basically, it's a very long wire that is wrapped around itself, through which we put current on one end and goes on the other. And because every wire generates a magnetic field when there's current through it, we're going to generate a magnetic field that is very big because we have a lot of wire. Okay?
Yes. You will see that a coil, this one is metal, and you will say how it's not making the short path between all the metals. Because actually that metal coil is isolated with a resin on top, a transparent clear resin.
Exactly.
So actually, imagine that it's the same as a cable protected with plastic, but in this case, it's a super, super thin and a small layer of plastic epoxy covering around the metal, so actually it doesn't use space in the wrapping of the coil, and we don't need to make one that is double size. Mm-hmm. But this is the same as having a really, really long wire. We have plastic sleeve, but we don't see the plastic sleeve. It's a cover isolating epoxy on top of the metal wire.
Mm-hmm. So the idea is that what can we control from our microcontrollers? We know that we can basically voltage, right? This is the only thing that we can manage. We can manage through voltage. We can open switches. We can open whatever other things, and that allows current flow. Basically, we can turn on a light from our microcontroller by using, for instance, a MOSFET or a normal switch, etc. But the only thing we can do is control voltage. If by means that we will see today, we are able to control the amount of current that goes in this coil, we will be able to control the magnetic field that is around it, and then this coil will be as a magnet that we can control. And then we can, for instance, move things. Okay, what type of things can we do with it? Well, first, yeah, the material of the wire of the coil, it's something that is conductive in general.
That depends. For example, for audio application, is gold because it's way better conductor, but it's more expensive. But you want to have like that small change in the conductivity with gold. Actually, in audio, it's usually gold cable. In normal motors, it's copper. In, let's say, cheaper devices, it could be aluminum, for example. So actually, the metal depends on like how high-end cost the application is.
So, well, the idea is that it's a conductor, and a conductor, by definition, is a material that has very, very low resistance per length. Yep. So at the end, there will be some resistance, but it's so tiny that at the end it conducts all the electricity, all the current, and without any loss. That's it. So what do we do here then? It's, in this case, we have two coils. Remember that this one on the left side and on the right side there, they act as a magnet. And in here in the middle, we have a magnet, a real magnet, the ones that the material, that is in itself polarized already. And if we imagine that we're able to put the material inside that has a way to rotate, or to spin it in itself. Maybe there's a shaft, and on one side we put the north side of the magnet, and on the other side we put the south. And then we apply some current to this coil. What this is going to try is to align itself, to align the magnet to the south side. So imagine that, can you put an N on the left and an S on the right? So all of a sudden we have a magnet that we can control and a magnet inside of it. And on the left side, we have the north pole that we can control. So the south is going to be aligned to this side. And then the south pole is going to be connected to the north. Let's say north and south is like positive and negative in magnets. It's just the convention. But basically it's that the positive is going to be aligned with the negative, and the negative is going to be aligned with the positive. Now imagine that we're able to alternate that. And we change the north to the south, the north to the south, all that, like constantly. So we change and alternate that position of the magnet that we control. And then all of a sudden we have something in the middle that is spinning. And we have just created our first motor. In here, in principle, we will see that, but the idea is that there's a circuit called H-bridge that basically is able to send current from positive to negative or from negative to positive. We'll see later, but it's the most common, let's say, circuit for controlling motors. That is basically a set of diodes that, depending on how we apply voltage on the two terminals, it will conduct on one way or on the other.
Okay. Normal DC motors, there are some mechanical touching devices that they change automatically all the time the direction of the current based on the rotation. So actually, the moment you start, you need an initial impulse, and then it will start switching automatically. It's like basically, it's like think of a metronome, but in a small scale with positive and negative.
No, an alternator is something different. An alternator is something that generates current from movement. It's, for instance, what you have on your on normal cars, that when it spins, it does the opposite effect actually, and it's able to magnet induction can be from current to magnetic field, and it can be from the other way. So it can be from magnetic field to current. They're not exactly the same, but the idea is that you can use the same setup to generate movement from electricity, or from electricity, or from movement generate electricity. That's the idea of a motor or a generator. Yeah? More or less.
DC motor can be an alternator, yes. The design is slightly different, so it's not as efficient. And an alternator can be a DC motor, kind of. But like the base concept is exactly the same.
And the idea, if you, in current state of the art, you can do this, and you will see maybe some concepts, they're not like for the class, but they're just related to this, which is, sorry, it's like very uncomfortable to look at you with this image. Is the concept of, in new cars, is called regenerative braking, which basically you have motors on the wheels, electric motors that impulse the car. But when you brake, you don't brake with normal clamps. And by that, you're just wasting energy because you're just heating up a piece of metal and dissipating heat. You use the same motors, but in the inverse way. So you generate electricity back again. So you move the car, and when you have to brake, instead of using something that evaporate friction, you just invert the motors, let's say, and they generate electricity, and you can put it back on your batteries. And imagine that how smart this could be, that if you know, for instance, that you're going to go, you're I don't know, 2,000 meters high, and you know that you're going to go down, and you're going to use a lot of energy to brake. Imagine that your battery is low. You would say, okay, I don't care about my battery because I know that from 2,000 to 0 meters, I'm going to be charging the battery by using regenerative braking. So you could do very complex things with it. And there's a lot of people working on this thing. I think also Clement was working in that topic the past. I don't know, Clement, if you want to say some words, but that's the idea.
I mean, you explained it perfectly.
Yeah. Inertia. This is its own inertia. So the idea is that this shaft is going to be like, you want to reduce as much friction as you can. And at the beginning, as Edu said, you have to crank it a little bit, and then it just stays spinning. And a little bit of inertia allows you to, let's say, realign again. So you pass a little bit further, and then you change. So it's not perfectly aligned, and it goes to the other side, let's say.
You mean instead of rotating clockwise, start rotating counterclockwise? Actually, to do that, you need to stop the movement and then invert. Instead of starting positive, negative, start negative, positive. Yes, it's the same pattern, but the first, let's say, shacking to actually get the movement is the opposite. So the first movement is the one that is going to define the rest. Exactly. So actually, if you have the current that's not enough to make the initial movement, you know that when you have a resistance at the start, it's higher than the rest of the movement. So actually, if you initiate the movement manually in one direction, it will spin that direction. If you initiate in the other one, it will spin that direction. If you are running the motor at the bare minimum.
Estaba pensando en una cagada que he hecho. No pasa nada. Okay, so then solenoids. So the idea is that we're going to try to take the most simple element, which is just our coil, and see what happens. So the idea is that we have, let's say, our wiring. This is just as if we cut this in a, let's say, in a perpendicular way. And we just put current through it, and this is the magnetic field that we generate, okay? Then, if we imagine that we put something in the middle, and that something is a piece of metal, a metal cylinder, that metal cylinder is going to be pushed by the magnetic field, the same way as the magnet on your fridge is attracted to the door of your fridge, right? And that you could use, for instance, to open a switch. And if you encapsulate that in a blue case, then you have a relay. Okay, so basically a relay is just that. It's a coil with a piece of metal inside that when you put electricity into the coil, it's going to generate some magnetic field, and it's going to attract or repel that little cylinder, and it's going to move a little switch. So it's going to press on a little switch with a little bit more complexity, with a spring here on the top, so that it opens or closes the circuit. And that is, for instance, why when you use a relay, it sounds. When you open, it clicks. It does like, because it's this little thing is opening or closing, and what is happening inside is just that. Okay?
Actually, this system works exactly the same in all your houses. When you ring the bell, it's actually this, that in the moment it touches, it gets disconnected the circuit. So actually it's doing at really high frequency. That's why the ring bells like, because it's opening and closing really fast. But basically it's a coil with a close contact like this. Then the moment it closes, breaks the circuit, so automatically self-turn down.
Okay. So this is how they look normally. Well, I think that you're already experts in relays. Just keep in mind that relays, they don't work for absolutely everything. You have to read either the data sheet or on top of it, and it specifies how much current they can cut and in which conditions. So it's not always that it can open DC or AC no matter what. But actually, just think that here, this part, when there's a lot of current or voltage, they're going to attract each other as well, and they stay stuck. So that it's important to see the limitations of the relay, so that you try to open something and they don't open because they just are closed, and the magnet is not able to open this thing here.
Yeah. When you conduce really high current through a cable, it gets hot. That happens also with the terminals. They can get so hot that they can melt together. That case is damage. So they have a specification. Also, these devices, they cannot open and close super fast. They can do it more or less around like 1/4 a second, the fast and close of opening. If you run it faster, they break because basically they're working with a mechanical part moving. And they have a due life of around 100,000 cycles in average. So above that, you will need to replace them.
Okay. So other types of relays, they're not the same, but just for you to see, and so that they sound familiar, is not a relay like this one that opens or closes a switch mechanically, but it's what we call solid state relay. That are normally SSRs, I don't know, some people call it either way, and they look like this, or they have a normally, well, a very different packaging, something.
Me pasó lo mismo.
Okay, and the idea is that we have something like this, but sometimes they look more like this. Okay, and basically what we have inside is a circuit like this one. Super simple, just an LED and what we would call a phototransistor. It's a phototransistor, yeah. That basically, when we turn on the relay, an LED emits light and affects a secondary circuit that is not attached to it. So it's physically in the same, under the same enclosure, but they are not part of the same circuitry. That is the power control area that will open or close a phototransistor. And by that will allow the current, or well, the current flow in the, let's say, power part. So in the biggest area, right? If you turn off the LED, then the phototransistor turns off. Ideally, this is better for the concept of what is called galvanic isolation, which is the idea of separating the, let's say, different circuits that do different purposes on your electronics. For instance, the high power or the power part, and the low power or control part into different circuits so that they don't affect each other. And they're basically separated in total different circuits, only connected by light, let's say. That's why also normally they are black, so that there's no light coming in and affecting the phototransistor. And just that. Okay. Do you have anything?
Why don't we use directly a transistor?
A transistor?
Yeah. Like why the left circuit would not just bring current into the interior of the transistor and let the current flow?
Electrical noise. So you have usually happens when you have a really low, really sensible circuit, let's say microcontroller or whatever, and a really high voltage with a lot of current circuit that can have electrical noise. And maybe you don't control, maybe you control, but the best way to actually separate them and not have one influence each other is to actually have them separated completely.
So it's the idea.
Instead of having electricity to activate, is basically imagine the same as in the boats that you use light to actually transmit between the boats before in the work. It's exactly the same. So, and the good point is actually light is really fast. Actually, we can activate and deactivate really, really fast at the speed of light.
So the idea is that, imagine that this component here, it's a switch that is only actuated by light. So when you put light on it, it opens. When you turn off the lights, so there's no light on it, it closes. So it's just a switch that you don't have to touch, or you don't control with voltage or anything. You control it with light. The idea is that the concept of this galvanic isolation which is I have my microcontroller that is very low voltage, very sensitive to noise, and like delicate, and something that is a little bit more rude and noisy and powerful, etc. That you don't need to be so clean, but that you don't want it connected to the delicate part, let's say. So you physically don't have any connection or no path for current to go from the high power part to the control part. Say. And the idea is that there's just light that connects both of them. And that way there's no way for noise to go from one side to the other.
Final output is almost the same as a relay, but more long-lasting, faster, and more expensive. It's way more expensive than a relay, but actually it does the same, but it's better in general. But also, as it's more complex to fabricate, everything is way more expensive.
Okay, some little comparison, and you can see here in this table and also in this link. But normally, electromechanical relays are slower, they're more noisy, and they don't have this concept of a galvanic isolation. And normally solid-state relays, they get hot, very hot.
So they are less stable.
SSRs, as solid-state relays, you need thermal management, let's say. So if they get too hot, they can even melt. Let's say the encapsulation can even, and that happens a lot. Me too.
Yeah, my 3D printer has solid-state relays, for example, it melted. What happened is actually the heaters never turned down until the printer reached 400 degrees that I disconnected from the plant.
Why would a ventilator most part of the time?
Or heat sinks or whatever.
Yeah.
But you need to actually trade them with love in general.
Mm-hmm.
They are more sensible, but they are dead.
It's because of the friction than the general.
There's no friction inside. Is that inside here the circuitry? I'm not expert in SSRs, but inside I guess that there's a lot of resistance by the like electric resistance, and that generates heat that is not dissipated, let's say, in any way into the copper or any other heat sink. I don't know if you know why they heat up so much. I don't know in particular why that happens. But either way, they are a good option if you don't have to do like very high switching or of high frequency and high power. High frequency you can do, but you have to, let's say, over dimension them so that they don't heat up and they don't basically stop working. Okay. I used at one point, I just saw you out of no. Yes, to show, I made an installation once like this one a couple of years back. But the idea was that they were projecting onto coins, let's say, onto like old coins from Franco and kings in whatever, like a little bit of like criticism on the monarchy and things like this. And they were like shining like different and making projections, okay? These are lights that are normal LEDs, but that consume a lot of current, in this case because they were very powerful, and I used solid-state relays to control them with a small Arduino to control, I don't know, up to 20 lights or something like that. Okay, and they were in a room all dark and making these projections. Then this later on went to Chile, and instead of you're from Uruguay, Bolivia. Okay, but well, in Chile 2 years ago. Okay, so 2 years ago there were almost 1 year still. There were a lot of riots in Chile, and the police were using actual bullets to dissipate the riots. And the artist collected all the bullets that were left in the streets and made an installation out of that as a protest. And he made like a nice sculpture out of that. So you see that these things, and Edu uses them on printers and robots and things like that, and you can use them, let's say. Okay, so that's it for, let's say, the control of a magnetic field using, let's say, coils as simple elements. Before going into a little deeper into motors, let's talk about this concept that you love, that is called PWM. Okay, so it's already there, but let's try to define this together. So, what is PWM and what is it used for? Who can give us some insights about it? PWM, what is it and what is it used for?
First, what kind of output we can have? Digital and analog, no? A digital output, what is? 0 or 1, no? 0 voltage or maximum voltage of the circuit you have. An analog could be something in between, it's a gradient. We can grade and just put half of it, 1/4, etc. So PWM is a type of digital signal. We just have zeros and ones. How we can make, for example, a motor work at half of the speed or LED at half of the brightness with a digital signal if we just have 0 and 1?
You have the digital signal on the stuff.
So actually what we can do is control the timing of on and off at really, really high speed. For example, with light, it's really easy. Humans, we see constant illumination or constant movement above 22 frames per second. So if you can blink faster than that, you will perceive that it has like continuity. With motors, it's slightly the same concept, but it's slightly different. So with PWM, actually what we know we can control is have them on for just a really blink of microsecond and turn off for a controlled time frame. And repeat that at really high speed. So we just on, off, off, on, off, off, on, off. That will be running the motor really slow. If you spend more time on than off, you are running more than half of the threshold. Meanwhile, if you spend a lot of time in on and little time in off, it's almost running at the highest one. Meanwhile, at all the time in on is full blast. But basically, it's like having on and off control, but with time frame. That is simply, really, really simplified PWM.
I think the idea is that you can see this in this animation, and on the left side you have on-off pulses, which is basically what we can control from a microcontroller. And we know this, that we only have 5 or 0, true, false, high or low, just 2 levels, binary, remember? And that how are we able to generate something in between? Well, we fake it. And we fake it by tricking that the real life, that the real systems have inertia, and they don't accept only binaries, but that they still have some, they take the average of what we send them, and they try to make up for what they receive on an average way. So on the left side, you have what we send them as a pulse trains, let's say, like on, off at different widths. And on the right side, we see what is the average of that voltage or of that signal through a period of time. This we see, for instance, I was saying, for instance, on lights. These fluorescent lights or any other lights are actually flickering, but you don't see that because they go so fast and they appear to be like a foot blast. But if they were flickering a little bit slower, then you will start to see, but on average, you still see that they are bright enough, right?
Yeah, exactly.
Exactly.
The frequency of the sensor is working at the, like, it's time framing with the light frequency. That depends on the camera. That's what depends, like if your phone or your camera is set up in United States mode, it's at 50, and we are at 60. Actually, you will actually see the flickering. So you need to set up to work at the same one so you don't get that effect. So actually, we see continuity, but aliens come to visit at some point and they see at 120 frames per second, you will see this guys are crazy. Why they have the lights on and off all the time?
Yeah. And the other thing is that LEDs, for instance, sorry, yeah.
Just the frequency at which we have to run this all we know for motors, so that it's fast enough to work.
So at the end, what you want to do is get average voltage level. And I don't know if I fully understand the question, but
¿Cómo controlas la frecuencia?
If you do that at 1 hertz, it will not work for the control and motor.
okay,
So up to which frequency do we have to go so that it works?
that I never asked myself.
With motors, it's tricky. Actually, for example, huge motors, you cannot run PWM. You need to do like fake PWM, but maybe the on pulse is for 1 second. Because the bigger the motor, the more inertia it is, more actually time it needs to be on to actually start rotation. So I did an installation with fans, like normal fans for summer. And actually the motors were huge and heavy. So actually I was making PWM, but instead of being milliseconds time between on off, it was like 1 second off, 1 second on, changing the variation between 1 and 5 seconds. So actually it was is put with modulation, but the time frame is way bigger. In general, this doesn't happen unless you're working with really archaic systems like DC motors that they are really, really basic devices. Now everything, we can run it really, really fast at really high frequencies. That will still work.
I don't know to answer fully the question, I don't know the exact answer, but I think that is more related to the frequency that you can run it from your microcontroller, and the physics or the other motors, except that they are like something specific like big. It will depend on either if you have MOSFETs running them, because at the end you don't directly control the motor from your microcontroller. You need a MOSFET and another power supply. So it will be depending on the switching speed of the MOSFET and the microcontroller speed, as far as I understand it. And not all the microcontroller pins will be able to do that in a fast way, and not all the pins have that capability. Actually, you need to look for pins that are able to switch, and normally in Arduinos are marked with PWM or this little tilde, like the Enya, which is the PWM capability. As far as in the motor, I don't know if there is any restriction. You know much better than I do for this.
Depends a lot on the motor.
There is data sheets or something like this for the motor that maybe you recommend to.
No, because you don't usually use like analog controlling devices. It's a way of controlling them, but they are not initially designed for that. That control. Actually, they overfit if you use using that application. The frequency of PWM, I just look for it, is around like 10 hertz. That most of the microcontrollers, even the most basic one, can run with 10 hertz. Yeah. Like for example,
even for a small DC to regulate the speed, or
yeah, with a small DC, like you can run them with PWM, no problem.
And that frequency as well to
Yeah.
regulate the.
You need to change the PWM time frame when you are become like larger system, especially with that have way more inertia.
Okay. So any questions before about this? The idea, I think this is like the best exercise on how to see this is to try to do this with an Arduino and fade an LED. Like do some waves by controlling the on-off pulses and see how you can visibly see the fading of the intensity on the LED, which is directly related to how much voltage difference there is in between the terminals, and because of that, how much current flows through it. Okay.
Arduino example, basic.
Okay. Now, this is just a reference, and probably we will talk more about this tomorrow, about PIDs, if we have time. Yeah, we have time tomorrow, or no?
Okay.
Okay. But you will hear this idea about PIDs, which are say controllers. Just here, small note. What do they do? Basically, they're used for controlling things when we have information from the environment that we can feed back into our system so that we can correct based on that extra information. For instance, imagine that we want to regulate the sample that I always put, the temperature of this room, and that we have our algorithm that we used to do like a threshold. If it's over, we turn on the heat, and if it's below the threshold, we turn on the heat, and if it's over the threshold, we turn it off. Right? Now imagine that we had a system that is not just on-off, but that we can regulate how much power we could put in the heat so that we can always be around the target temperature and not only oscillating and letting the system cool down and then heat up and then cool down, but something a little bit smarter. For that, we need information, which is a temperature sensor, and a way to actuate on the system, which is the power that we put in the heating system, okay? Based on those two measurements and our offset or our target temperature, we would be able to determine what is the error that we currently have. Based on only where do we want to go and what is the measurement that we get. The difference between them is the error. It's as simple as that. Now, what happens if we can, one way we could think about it is that we can regulate our heating system based on how big the error is. The bigger the error is, the more power I put. And that will, let's say, make our system stabilize at some point, but that probably could lead to, as you can imagine, if the system has a lot of inertia, to do what we call an overshoot, which is basically passing over the threshold and maybe making an error that was positive on one side, making an error negative, and then positive and then negative, and we oscillate all the time. Because we just based on something very simple that the bigger the error it is, the more power I put. Other two concepts that we could put in here is that based on how much error I accumulate over time, or based on if the error is increasing or decreasing, so if I am very close to the target or not very close, I can tweak those parameters and make a better system that if you make a perfect thing, like just make a perfect approximation. Something like that. So that prevents overshoot, so that doesn't oscillate, that stays on the target, and it doesn't take that much time to get to what we actually want. That is in the field of control theory. We will talk a little bit about that tomorrow with an example that Edu made for controlling exactly temperature with a PID controller, but that is more or less the idea. So basically what you want to do is measure something, have your target and a way to actuate on it that is not just, let's say, on-off, but that has some, let's say, regulation into which you can actuate by using these different parameters like that are depending on the error that you have, okay? Again, this is just as a concept. I don't want you to know about PID controllers after this explanation, but that if anyone says, what is I need a PID, that it doesn't sound like, I don't know, is that a study, are they going to study in somewhere, or I don't know, yeah? And that's it. So,
to summarize, is we have different ways of controlling things. On and off, when a condition happens, on doing with algorithm and doing kind of preventive way. The same as, for example, in that you make a fire to heat your house, even if the fire is still off, it still heats up for a bit of the night. Actually, we can prevent, if we have sensors, we can read this and do like smart control, if you want to call it, that is preventive algorithm that proportionally, iterative, and derivate, that they do this based on the sensor acquisition and on time. So actually, they prevent to go above and lower than the threshold that you set up. So actually, they keep a clean output exactly in the point that you wanted.
okay. So now time has come. We're going to start to talk about motors. Okay. We're gonna do, let's say, a little bit theoretical at the beginning, because I think this has to apply for here, but in everything. Let's say that is learn how to think, but not to memorize things. Okay, and then we will see things I think start making sense better when you approach them this way. Okay, so I'm going to talk a little bit about that idea, or the idea behind motors, and then we'll go into each of the different cases. But you'll see that motors have a lot of variables, and if you try to memorize them all at the beginning or try to get your head around them, they sound very illogic, and it's probably better to just have some concepts, try to understand them, and little by little gain that intuition based on those basic concepts, so that we can make like layers of abstraction. Okay, so a motor is basically something like what we saw here, that is a device that has internally some magnetic elements, either controlled by us or ferromagnetic elements, that are generating some motion. Okay. Now, there are two concepts in motors, or things that move in a rotational way, that are important. First one is torque, and the second one is speed. And they are not related to each other. Okay, they are independent from each other. The torque is basically what we could call like the rotational force. It's like if I twist my arm like this, how strong my rotation is. Okay, how much I am able to twist something. For instance, for me it's very easy to do this on the bottle, and I am applying some torque, but it's impossible for me to actually do that on the metal. Okay, I have to apply a lot of force, but not to do this. Okay.
So it's the force. I'm not that sorry, but it's the force exercised on the rotation, or the force that is generated by the rotation.
They're intrinsically related by Newton. So you cannot. Every action has a reaction. So if you generate a force, there has to be something that counteracts it. Otherwise, there's no force.
It's the value of that force, whether it's generated by the rotation or it's the consequence.
Yeah. So basically, imagine if I have a motor. Let's say, just imagine a motor and no concept. If I don't put anything that breaks it, that holds the motor in place, the motor has no torque. It's generating no torque. It's just like spinning with zero force, so zero rotational force. Why? Because there's nothing to stop it. If I try to hold the motor, then it will actually need to fight that as a reaction, and it will generate some torque. Otherwise, the motor is not generating anything. So the idea is that every action has a reaction, and it's actually the third point. And Newton is not Newton, it's Newton. If there is no load, the motor will not make it up. It will just adapt to where it's connected. And sometimes that load will be so big that the motor cannot counteract it, and basically it will stop.
Or burn.
Yeah.
The cars, no?
Sorry?
When we were doing the cars, sorry, not cars, the machines with the arms,
Uh-huh.
the machinery, when there was a weight, when there was too much weight and there was not enough torque, it wouldn't move forward for this reason, because there wasn't enough weight.
Exactly. Actually, what happened in that case is we are not generating movement. That is what keeps the motor cold. What it does is overheats, transforms all the lack of movement into heat that finally goes to a teardown of the motor or burn it.
Okay. So the other thing, so two basic ideas, torque and rotational speed. Rotational speed is as simple as how fast it's rotating, okay? You will see that units for these things, torque can be Newton meters. So it's basically a force and a distance, because you have some leverage, you have some possibility, like some possibility to make something rotate by some sort of lever. And speed is normally, or RPMs, which are rotations per minute, how many turns does it make per minute, or radians per second, and things like this. Okay? Now, how are these two basic physical things of the motor related to what the things that we can control, which are voltage and current? So let's think. What is making the motor rotate? Sorry? But what principle, let's say, is
the more strength you need, the more speed you want to aspire, the more voltage.
Okay, but going a little bit further before, let's say the principle that it's making rotate the motor is just magnetism, right? We are controlling, yeah, we are aligning two magnets, let's say. So the magnet, probably, yeah, I think is that there's how can we modify the power of that magnet? The number of coils, for instance, and for something that we can control, is it the amount of current that we put will modify how strong that magnetic field is, right? So if you think that how much, if we put more current, we generate more magnetic field is going to make the motor have more torque. Exactly. So more current normally implies more torque. Okay, implies that to regulate how strong the magnets are going to be held together, you need to put more current, and that doesn't come from nowhere. You have to either put a power supply that is able to give the amount of current that the motor needs, and then you have to be able to cut it with whatever switch, MOSFET, or element that you put in the middle. Okay. The other concept, rotational speed. Inside the motor, you have to think that when you rotate the motor inside, so you have the magnet and then the coils that you rotate, you are generating a magnetic field, and then there's what we call a backward magnetic field that is generated as a counteraction, because they are this one is generating a magnetic field, and then this other one has its no magnetic field. The difference is what we call the back MF, or back electromagnetic field, which is basically how much is left from the interaction of both. If we want to regulate the speed of the motor, meaning how much difference do we have in extra so that the motor doesn't stop, then we can regulate how much, I'm explaining it very badly, but that magnetic field is related to how much voltage do we put. So if we want to regulate how fast the motor turns, we have to regulate how much voltage we put in the motor. Then, I mean, it's probably a little bit difficult to visualize, but the idea is that inside the motor, you will see something that is called like that, back MF. That is, let's say, a magnetic field that is generated inside the motor just by rotation. That magnetic field is related to voltage, and you have to apply more voltage to be able to cope with that magnetic field. So to be able to rotate faster, you need to apply more voltage. This means that, yeah, this drawing, I don't understand. You want to go to the other one?
I think we got hung up because you said that the coils are the things that are rotating. Right?
Depends on the motor. Sometimes are the coils, and sometimes are the magnets inside. So, I mean, what are you doing?
Dos polos o cuatro polos. Pero también un movimiento lo hace una media vuelta.
Ajá.
Pues también influye el diseño del motor.
Okay. ¿Quieres explicar? No sé por dónde. No. Ya está. So, to summarize, current means more magnetic field. More magnetic field means more strength in the coils, and how much they attract to each other. Then it means more torque. So current is directly related to torque as a generic thing in motors. Not always we could apply more current. We'll see that each motor has its different characteristics. I don't understand that. But on the other hand, the magnetic field, this back MF that is generated inside the motor as a difference between the magnet, the permanent magnet, and the magnet that we control, is bigger or is related to voltage that we apply into the motor. And because of that, applying more voltage, we will generate a bigger difference, and by that, the motor will spin faster. Okay? This means that voltage is related to speed. So if we want a motor to spin faster, we need to apply more voltage up to its limit. If we want to spin lower, we have to decrease it. And the opposite more current for the torque. Yeah.
Since there's a relationship between voltage and current, like the resistance, or like how do you manage to play on? If you want more torque but less speed.
That depends on motor design.
That depends on the resistance of the motor itself.
Exactly. So that depends. That's why some motors, for example, they have, what they do is like they have 1,000 turns with a really, really thin cable that can only transmit X amount of current, dissipate the current. In that case, we have a really, really very thin cable, but wrap around billion times. And then with larger torque motors, we have a really thick cable, be able to actually afford the dissipation of really big amount of current that has just 3 rounds around. So you just wrap 3 times, for example. And this is just making up the numbers, no? But a small, let's say a swimming pool motor for like the cleaning, usually it's a motor with really thick cables, you just wrap around like 10 times because it needs a lot of torque but rotates really slow. Also, that influences the amount of poles. As the simpler motor you can do is like have 2 coils and just 1 magnet. In the moment you change the polarity, it just makes half turn. We can also increase this by multiplying the number of coils and poles. That means for just a small change in the voltage direction, we just can rotate, in this case, 1/4 turn. So actually we can have like 1 pole, let's say 2 poles, or we can have like 48 poles. That means each movement is smaller. That means usually those motors are more for precision control and slow movements, but with more torque than the other ones. It's a balance between poles versus number of wrapping of the coils versus also like thickness of the coil. And all these 3 data influences in the motor design. Actually, it's like there are more things related, but these are the big 3 ones. But in general, we don't design the motors. We just look for a specification of the motor, this torque and this speed. And the manufacturer just made all the magic of coil, turn, thickness of cables, etc. Actually, when a motor burns, it's because if you are using, for example, a really thin cable cannot dissipate a lot of heat. So actually, what happens is the cable burns itself because it's not able to afford that heat dissipation because a really thin cable cannot have that amount of current transmission.
What you're explaining, sorry, but like what you're explaining now is related to V equals CR. So the formula that we do usually calculate resistance and current.
Yeah, ohms law.
It's related to that.
Yeah.
Like we can use it in the same logic. The more resistance we have, and then if we want less current, then we have.
Exactly.
Now, well, the idea for this is not to displaying all motors, but to have this idea that imagine what Edu was saying. What happens if we have a motor that has a lot of coil turns? So there's a lot of wire in it. What's going to happen?
Lot of resistance.
But also a lot of resistance. So that's a motor that with a lot of current is going to overheat. Okay. But then also what happens if in this sense of, is it going to be a lot of torque or less torque? That a motor that has a lot of coil turns. Come back to the basics. So imagine the magnetic field is going to be larger or smaller. Okay. And how much torque is it going to have more or less torque?
More.
Yeah.
It'll be able to handle more current, so it should have more torque.
So, but it's not only because of the current, it's because it has more turns. Just because of that, at the same current than a smaller one, the magnetic field that it can generate is bigger. No? Do you agree or not? Yeah, so then more magnetic field, there's more magnetic field. Just imagine like something that is able to attract something else. So more magnetic field, more attraction. More attraction means more torque. Yeah. Let's talk. Let's talk a little bit about another concept before we go into motor control or the different types of motor that Edu will do. So how do we control motors? And for this, we need to talk about this concept or this device that we've been always mentioning in almost every class already, about MOSFETs. So today is the day that we understand what a MOSFET is, okay? So you remember the idea of a transistor, right? This is the small device that basically is made out of a semiconductor that we can control, and that with very small currents, we can regulate very big currents, okay? MOSFETs are a type of transistors, but that they are made out of different materials and that have different capabilities than normal, what we call BJTs. BJTs are the ones that I explained at the beginning that are bipolar junction transistors. Just basic transistors that the only thing that they can do is just with very small current, they can regulate a larger one, but the difference that they can control is not very big. It's just like they're used for very small circuits. The voltage difference that they can handle is very small. A MOSFET is actually two things. FET is field effect transistor, and MOS is metal oxide. So the combination of these two is basically the same as the transistor, but that can regulate with very, very small amounts of voltage or current, can regulate very big amounts of currents and voltage. For instance, with 5 volts or 3.3, you are able to regulate 30 volts and 16 amps. 16 amps is already a big electric shock that could basically kill you. And 30 volts is, if you think of it, is 5 times more larger than the input that we have on the controlling side. Now, if you want to read a little bit, you'll see that there are some things here about MOSFETs. If you want to read and you have some free time, I really recommend this website. It doesn't look good, but it doesn't matter. It's probably gonna explain everything you need to know about electronics. And in particular, it has something very interesting about semiconductors, talking about diodes, MOSFETs, and BJTs. And basically, they explain how they work in a very concise way. It's really verbose, let's say. It has a lot of stuff. But if you really want to understand how these things work internally, these are a really good explanation. Okay, I'm gonna simplify it a little bit, and I just refer you to that explanation if you feel like spending some time into it. Two important things that we have to remember about MOSFETs. First, how they are constructed. There are two types of MOSFETs, what we call NPN or PNP, or N-channel MOSFETs or P-channel MOSFETs. NPN are MOSFETs, you can think as a MOSFET as a sandwich of two different types of semiconductors, N types and P types. N type, yeah.
Does anybody know what a MOSFET does?
Without writing, it's low voltage to, not writing, but the transfer low voltage to the values of voltage.
With small mounted amounts of current or voltage, we can.
Comparando con un regulador.
No.
Like a relay.
It is.
It's a switch.
Yeah, I think it was just like.
Yes, it's a switch. A MOSFET has the same function as a relay, but it does in a completely different way in the inside. To simplify.
So the application is the same.
Huh?
It's the same application.
Let's say if your purpose is to turn on and off something, you can choose a relay, an SSR, or a MOSFET. But you will need to choose between these three, depends on what is your application and what is your final output. But doesn't regulate from high voltage to low voltage and from low voltage to high voltage. No, it's a switch. A MOSFET is basically a switch.
Yeah, but with I think what I understood, or probably we understood it differently, but with a small voltage, you can, let's say, control or open or close or big voltage. Yeah.
But
So-
you can use ultimate mod, the PWM.
So with a MOSFET, you could do PWM. Yeah, but PWM, sorry, is I'm sorry if there's a lot of different concepts. They will all make sense when we start talking about actual motors in a second. But basically, a MOSFET is the device, and PWM is the technique that we use to make average voltage from digital signals, let's say.
Right. I'm just trying to think, like, is it like a light switch on and off, or is it like a slider on and off?
No, this is a light switch on and off. Yeah. Ideal, well, normally they are intended to be like that. Yeah. Okay, super briefly, I think it's interesting to know how this works, at least for me. But basically, semiconductors, you have two types of semiconductors, are materials that conduct under certain circumstances, okay? N types and P types. N types are negatively doped, and P types are positively doped, are semiconductors that have more electrons or have less electrons, okay? The interesting things about them is that between different types of semiconductors, or between N and P, things don't work. They don't conduct. They are super good isolators. So there's no electricity flow in this, what we call depletion zone, which is basically this area between an N and a P type. There's no, it's like rubber. There's no conduction. The electrons cannot jump from one side to another. But they do when they are the same, from N to N or from P to P, they do actually conduct. So what happens in a MOSFET that normally you have seen it more like this, they have three legs. One leg is called the gate. The gate is the one that you actuate on, which is the one that you connect to your microcontroller. And then you have two other ones, drain and source. We'll see that in which direction they are connected. But basically the idea is, if you apply voltage on it, what you will do is that the electrons that you have in this area, in the P type, they will all go to the gate, and you will generate some like polarity in it. And basically you will make like a bridge. Like you will accumulate electrons in here on the left side, and it will become like an N-type semiconductor. And remember, semiconductors N and P, they don't conduct, but N with N, that does conduct. So all of a sudden you have a small wire in here that you have controlled with voltage. The more voltage you apply, the bigger that wire is going to be, the less resistance it has. Normally, they are thought of just as on and off switches. And if you look for MOSFETs, you have to find several, let's say, specifications on them. I'm just going to look the ones that we have in the inventory here. But basically, MOSFET, this one. This is a MOSFET N channel, okay, 50 volts, 16 amp, of the size of this thing. Okay, so this can cut up to 16 amps and 50 volts. It's quite a massive amount of electricity.
What does the N stands for here?
N is the N channel MOSFET. There are exactly.
Otherwise it would be
P. Exactly. Yep. So then you see that it has 3 legs. This is not a leg. There's 1 leg, 2 legs, and then this other one. This one is very big because it needs to dissipate heat onto the, let's say, the copper plate on your PCB. And you see that there are in the MOSFET a lot of things that, a lot of parameters. First of all, it's an N channel. Second is a MOSFET, that's good. That is the maximum voltage that it can go from top to bottom, so from drain to source. We can stop up to 50 volts. So drain to source voltage. We have a continuous current that is 16 amps, which is a lot of current. And then here you have something that is called the drive voltage. The drive voltage in this case is 4 or 5 volts, which means how much voltage do we have to put in the gate so that this happens, this state happens. And at least we have to put 4 or 5 volts so that it turns on. Sometimes they will also work at 3.3. But what happens is that you will have a thinner wire here. So then the MOSFET is going to heat up because thinner wire means more resistance at the same current level, more heat dissipation. So it's not properly dimensioned. And in this case, let's say the width of the wire is not big enough, okay? Actually, no, sorry. BGS, I said that wrong. No, it's not drive voltage, it's BGS, which is 2 volts. In this case, BGS is the voltage that we have between the gate and the source. And sorry for that. It's not this one here. It's not drive voltage, it's BGS threshold, which is 2 volts, which means what is the difference that I have to put between gate and source? Normally source is connected to ground. So what is the difference that I have to put in gate? 5 volts, 2 volts, 3.3, so that these things happens. And in this case, it says 2 volts. 2 volts, and then the MOSFET will turn on. And then there's another thing that is called RDS on, which is the resistance between the drain and the source. So between both ends, this little wire that we have in here, when the MOSFET is on. So when we turn on the MOSFET, that is equivalent to a small resistor. What is the resistance of that thing? And it's 47 milliohms, which is very small. If you did the numbers, 47 milliohms at 16 amps times 0.047, that dissipates very small amount of energy, a very small amount of power. And this number comes from Joule's law, which is basically how much heat dissipation is generated by a resistance. So basically, how do we know that something is dissipating heat? Because we have some current going through and some resistance. And I actually did it wrong. So is the amount of current squared and then times the resistance, and that's how much heat is going to dissipate in watts, okay? And this number that we have here, if I'm doing that right, is 12 watts. It's not that big. It's already, it's gonna heat up. If you touch it with 16 amp, it's gonna be, no, but the idea is that you use this plating here so that you are able to dissipate that energy into the PCB. And sometimes even you might need to put a heat sink in the back, some small radiator, so that goes into the air, okay? But basically these are let's say the different, or the most important, let's say, parameters for MOSFETs, yeah.
More than 2 volts for BGS in the program.
No, actually this is the threshold. Below 2 volts is not gonna turn on. Over 2 volts is gonna turn on, yeah.
And the maximum is
Sorry?
The threshold is 4 volts?
2,
2.
yeah. Sorry, this, it's this value here, is BGS, okay? And you will always see this in any MOSFET datasheet, BGS, voltage from gate to source, and RDS on are the most important ones, as well as this one, BDSS, drain to source voltage, and the current that it can dissipate, okay? That's pretty much it. I just want to say that, remember, there are 2 types of MOSFETs, N types, so it's NPN, or P types, is PNP, and they don't work the same. You see that here in how do we actuate them. Basically, P channel MOSFETs are actuated on the opposite way of N channels. In the case of the N channel, we have to put, this is here on the left side is the gate. So we have to put voltage that is different from the load. So from this value here, remember is the gate to source voltage. So we have to put some voltage in here so that the load is going to receive some current. On the P channel MOSFET is the opposite. The difference is between the gate and the drain here. So they are the opposite way. And basically, you have to turn them off or put a voltage that is low so that the MOSFET opens or closes, okay? Have a look at it in here, and when you actually implement it, you'll see the deal. You'll see what the difference has to be for this. But just remember that these devices are gonna be very useful to control, especially to amplify, let's say, the controlling side to a very big voltage and current to control motors, lights, or any other things that consume a lot of things. These things, that's one thing, they're only for DC. They don't apply for AC or the what you have in here. Okay. MOSFETs,
The N in the T is only for AC.
for DC, yeah. Okay. Here as well, I give you, this is probably my best cheat sheet in the world. I found this time ago when I did the academy. And this is the reference for electronics. And here they give you transistors and MOSFETs and what the different legs are in the different types of the different packages and how to connect them. As well as some other things, but I basically use this for my MOSFET cheat sheet, that's it. And you have it in here so that you see also for diodes and other things. Whenever you have some doubt, just go here, save it in your bookmarks, because I go to this every time I have to do some sort of design, and that's okay. Also you have LEDs and such. Okay. So maybe,
When do we use a relay and when do we use a MOSFET? A MOSFET is for motors?
no, MOSFET is for anything, but relays, you can use them also for AC. And normally they support much higher voltage and current.
Well, most of the SSR and relays are, you are driving the control with DC, and the actuation is AC. Some relays and some SSR, they also can work in DC, but not all of them. Actually, the blue one that use in Arduino kits, yes, they work with AC and DC. But for example, SSR in general, they only work with AC currents. Meanwhile, MOSFETs is only DC.
SSR is AC and MOSFET is DC.
Yeah.
If you want to close up, yes. Most of the SSRs are AC and most of the MOSFETs are DC.
Okay, so that's for that. Here are some examples on MOSFETs that I think is fine. So we talk about this. So we finish this and we take a break and then we talk about steppers. Okay. So we talk about this final concept about H bridges, which will allow us to invert the current on motors, and by that invert how they rotate. And then we'll take a break, however much time we need, and come back and start talking about servos and steppers and I don't know, whatever Edu wants to talk about. So now how can we use, or in what way could we use, could we control motors that basically they don't have a way to, let's say, like change rotation with circuits that actually work with always positive voltage. And by this, I mean that, for instance, a microcontroller or the power supply that you use in DC, you always have 5 volts and ground, and that's it. There's no negative. There's no below 5, and there's no way to do it in the microcontroller in itself. So for reversing the rotation of the motor, we need to actually be able to do that. So we need to be able to invert somehow how the current is going into the motor, either from positive to negative or from negative to positive. Okay? That is where this concept of H-bridge comes in. Okay? The idea is that we have our normal setup, voltage and ground, and we have a set of transistors that are controlled by 2 signals. One, that we could call it A and B, and that are placed in this way. Okay, just notice here that the transistors have the symbols are opposite. So the arrow here is on top, and then the arrow here is on the bottom. So it means that when I apply voltage in here, in this signal in here, I'm going to turn on this transistor, and this one is not going to be turned on, and the opposite on this one. Imagine that now I am able to say that A is 1 and B is 0, and then I do the opposite. So as you see in the animation here, if I turn on the A side and off the B side, then I'm gonna actually, let me just do this like that. So if I turn on the A side and the B side is 0, this MOSFET is on. So this MOSFET transistor, whatever we want to call it, is on. This one is on. So it's going from VCC to this negative pole of the motor, out of it for the positive, and then going to ground. And if I did the opposite, it will be the opposite way. So an H-bridge is a set of transistors with 2 inputs and power input that is going to allow us to control the rotation of DC motors and allow to control to which direction do they go to. We could also do that with PWM as well. Not this concept, but we could regulate the speed with the same circuit and use this idea of PWM as before by opening and closing these MOSFETs in a synchronized way so that we regulate the speed, knowing that we always have to do it in a, let's say, synchronized fashion. Okay. Yeah.
What did you say about PWM in this case?
No, that I'm just saying that H-bridge is just allowing us. So let's think about the three things that we can control in a motor: torque, speed, and direction. So PWM will allow us to control voltage, and by that we will control the speed. The torque is gonna be given by the current of the motor, and that is basically done by how the motor is made, and we won't be able to control it as much, because if you think of this circuit, the current is defined by the number of coils and how much resistance do we have in the circuit, and that's it. We don't have any actuation in it. And finally, the direction of the rotation. For doing that, what we can do is you build the circuit that normally they can package as well. We'll see a couple of examples now. And that is called an H-bridge. But you can combine both of them, H-bridge with PWM, and then you will have control of speed and direction. Yeah.
Actually, the same as, for example, if you rotate clockwise, you are running the H-bridge.
Huh?
So, no. So let's say you're running with the current, let's go blue. So you're running the current like this to rotate clockwise. You want to rotate counterclockwise, it's in direction. But at the same time that as we are using MOSFETs, transistors to do this, we can do it really fast. We can do, for example, for speed up, and in case we want to brake, we can just change the direction for a few seconds to give some touches and actually brake a little bit the motor, because it's going to try to rotate the other way, but we don't need to completely stop it. So actually you can use for accelerating and active braking, or just change the direction. Actually, how you control this process, you can do a lot of things with that.
Now, you could build your own H-bridge. At the end, the idea of H-bridge is you see the H, right? The same, you see it. It's an H, just that. You could do this replacing these transistors by virtually anything. It could be a relay, it could be a transistor, or you can just directly, as we say here, buy an integrated circuit in a package. And these are very common ones.
The MDF in the challenge of the machines, actually, some of you were already doing this with the relays. You were changing the direction of the DC motor with the relays. You were doing like relay H-bridge.
Okay. And normally they come, well, on different packaging. These are two very common ones that output current 1 ampere channel and 2 channels. So you could control up to 2 normal DC motors, or to control also, as we'll see in a second, a stepper. Yeah. Sometimes steppers, sometimes. Okay. So you'll see that even if they look as a microcontroller, just that's the packaging. And you will see that, well, these normal ones are very commonly used. These are the 293, and that have 2 inputs, 2 controlling inputs, 2 controlling outputs, and depending on the, actually, no, this has more, no? Logic pin 1, logic pin 2, 2 and 2, yeah. And then the power supply, and of course, the power supply of your controlling logic in here. So you need 5 volts from the microcontroller, and then the power supply for the motor. So this thing is already managing the power of the motor. So take care with it, because it's not just like a microcontroller. It also has an input for this voltage, which is the one that the motor is going to receive, and can be 12 volts, 5 volts, 30 volts. Yeah.
You were talking about energy braking. How to make sure that here in this case there is no energy flowing back in the circuit if it's driven for some.
What type of element allows current on one direction and not in the other? Exactly.
So you have
Either some of them already have, it's called back, I don't know if it's back current or reverse current protection. So I mean back current. Some of them already have them integrated in them. I don't know if in here we'll be able to see it in this one.
if you don't do that, there's a risk of screwing up the
Yeah.
controller.
Yeah, exactly.
Hello, actually, just happened to me 1 month ago. I was running like the scooter wheels, electric ones. Just, I was helping a friend in project to actually repurpose one of them and bought like it was basically a double H bridge to actually run them because it's slightly more complex, and we can do is measure actually has potentiometer to measure the speed and everything. So actually we're running them. We start running at a really high speed, let's say at the maximum. In the moment we release, actually just let it needle. There was so much accumulation of backward voltage that just basically blew up all the board with super big capacitors. Actually made it explode and make a little hole on the table. So we run a big motor at high speed, but happens actually. It's important to have the diodes for backward protection.
You are dangerous.
Yeah. So, well, with that, let's take a break if you don't have any other questions, and we come back in 15 after.
It's really important, just to clarify, these H bridges, they have different things. One is the control pins. It might happen like 1, 2, 3, 4, depends on the speed you use. The pins for the motor. The B motor power input, it means the main drain usually connected directly to the battery. But as a microcontroller, they also need their own electricity feeding that usually is running at the same as your microcontroller. Actually, you have usually 2 positives. One for the big power, and one just to power it as a microcontroller. That usually runs at 3.3 or 5 volts. That's you have it here, that is IC power, that is logic level power, just to power on the H bridge, and the other one is for the motor.
Exactly. So here you see, and actually, just to clarify here, so let's just go through all the pins. EN normally stands for enable, okay, on or off, the whole thing. Logic pin number 1, logic pin number 2, logic pin number 3, logic pin number 4. Here you have the table. The ones that come from the microcontroller. So these ones here that you connect to the microcontroller to decide on which rotation it is. And then voltage from the microcontroller that actually runs the whole thing at about like the circuitry of this in a control sense. And then the one that controls the actual motors. So the one that goes, that comes from the mains, let's say, or the big power source, not the microcontroller power source, the big power source, and that then is going to go to the motor. Yeah. You see also that these things are already out of 16 pins, they dedicate 4. So 25% of the pins are dedicated to ground and heatsink. And if you dedicate 4 pins into that, already should make you think that these things get hot because of the switching. So dissipate. Yeah. Motor terminal are the ones that go to the motor. So one of them goes to the one motor and the motor power supply, and the other one goes to. Is it like that, or is it because this is for 2 motors? ¿No? Será uno power supply y el otro terminal 1 y power supply en terminal 2, ¿o cómo?
No, va de todo interno. Tú conectas directamente a los pins aquí.
Ah, perdón, ese es el otro lado, sí, sí, sí.
So you have a motor.
No, que no me acordaba de los
You connect
4 y...
2 ends of the motor, and if you have another motor here, you connect
4i and 3i.
Yeah.
3y.
To these guys.
Yeah.
This one is for two motors. If you have a big battery, let's say 12 volts, the positive goes here. The negative, what is the negative?
Ground in the middle.
Huh?
Ground in the middle.
Okay, so this to this 4 actually. And if you have a microcontroller, let's say an Arduino, I don't care.
Arduino R.
We have the voltage that is the same as the Arduino. In this case, is 5 volts. The ground of both are connected to the same position. It's really important to connect the grounds. And we have then the data pins that is to control actually rotation of the motors. You can, okay, instead of making 4 wires, I will just connect both at the same time in the same position, okay? But you get the idea.
This is going to A. Sorry, just the lower ones are to A. But you get the point, it's fine. But they go to A.
So 1A and 2A for the first motor, and then for the other one for the second.
Yes.
Yeah.
You can run 2 motors individually in both directions.
And regulating speed as well. But you get how this works, right? It's just an H bridge inside, well, 2 H bridges, both that have internal transistors, big ones if they have to regulate and switch fast, and also control more like.
Can I ask you if there's a higher voltage, do you need more pins for the heat?
It doesn't always, no. No, it's going to be depending on the packaging. Sometimes they will have a big plate, like this one here.
But generally, like more surface area for the heat.
Exactly. And this one, the way that you achieve that is heat gets transferred by metal to metal conduction. And in this one, for instance, you have a big plate that you directly attach to something metallic, or with some like paste. How is this white paste called?
Thermal paste.
Thermal paste that basically helps with the heat dissipation. And normally you'll see if you open, not in the controllers, but if you open power supplies and things, you'll see that sometimes there are elements directly connected to the big plates on the enclosure that is normal metallic. Yeah, because of the solenoid, I remember.
These guys, they are really easy to, like in audio amplifications, you really can see these guys because they usually have almost the same package and they have a big metal heatsink that looks like a star connected to it.
And actually, just remembering that the thing that you put in there to attach that, actually you were doing what we just mentioned in here.
Was that, yeah.
At the very beginning is
because we had it switch directions.
It was this. So we were just there's no switching direction. It was just magnetic field or not magnetic field. So it's a coil. You put current into it, generates magnetic field, attracts a ball. If you release it, then the ball falls. But that's it. Yeah. So it's basically a solenoid that you just control with that. So let's take a break. See you in 10 minutes. If you can be at 20 after, if you don't mind, or 25 to start at 30 after.
Un par de preguntas. Primero, la imagen que has enseñado del transistor, ahora entiendo mucho mejor cómo conectarlo gracias al dibujo azul. Y me mola mucho entenderlo así. Después, sí, ahora entiendo por qué que quieres una diferencia de potencial aquí o aquí, por eso depende de dónde está conectado. Y siempre me preguntaba por qué había 3 patitas en el dibujo y en el transistor no. Y ahora, bueno, entiendo. Así que mola. Otra cosa, intentaba programar Arduino conectando el TXRX al Raspberry, pero alimentado a través de la fuente de alimentación. no me funcionaba.
Okay, because
Me estaba preguntando, porque puedo esperar un día en Nissan que alimentaba un EQ con la batería de un coche y flasheaba con otro, algo así. Eso vaya ground. Eso es obligatorio que el ground de X venga de la misma fuente.
Tienen que estar todos conectados.
Vale.
Sí, sí.
Dudaba, pero quería
Todos los grounds tienen siempre tiene que haber conexión de ground. Al final, por el ground lo único que hace es servirte de referencia. Es como el suelo.
Yo pienso 0, pero no es.
Es la referencia de voltaje. Sí. Esa referencia de voltaje podría ser 8 y entonces tienes 13. Entonces, si tu otro circuito es 0 y 5, esos 13, de hecho, hasta pueden quemar tu.
Basically, we're just moving a little bit and moving back in the direction.
La última cosa, pregunta más complicada. Me ha agobiado un poco con el tema de voltaje y todo, porque es una regla enorme. Tengo que leerlo y yo pensaba que sería un poco más sencillo. La pregunta es por
Claro. ¿Sabes? De hecho, piensa que simplemente puedes usar Arduino. Librería. La semana que viene usarás Wire para I2C. Dentro de 5 minutos usarás Servo, Stepper, NeoPixels. Siempre.
Es que para leer la señal es como el 7,5 menos que es. Ponemos un offset y lo reducimos a un poco más para que entre en el más 3 del ESP. Y eso yo pensaba que solo quitando el valor del offset va a funcionar, pero ellos hacen así filtro, gracias al filtro quitan la parte constante. No sé, a mí no me funcionaba bien y no sé si es porque no se puede quitar la parte constante o hacer un filtro solo es una cosa más precisa.
Me cuesta un poco visualizarlo, pero sí que esta tarde nos sentamos un rato y lo separamos. Pero bueno, igualmente, en cuanto responda a la pregunta inicial, puedes utilizar librerías sin ningún problema.
Solo que tendré que adaptarla al XP porque está muy pensado basado en el agua. Hay muchas cosas detrás que están especificadas para procesores. Igual mañana que ahora más tenemos el curso, pero igual mañana media horita tenemos. Ok, gracias.
okay.
Yeah. Yeah.
I have a question. Like, I somehow destroyed this hard disk, and just like, if you know anyone like that fixes these kind of things, because like pretty like important stuff on this.
We could try to open and see if it has another connector for like a direct connection to the memory. And Guillaume has a cable that you can connect there.
Okay.
So we have to find a way
If
to.
you open up, it doesn't destroy anything. Or
No, in principle it shouldn't. It's just an enclosure and it should be fine. But I don't know if it's gonna be easy to open. Yeah, maybe with some, you see, like a small spool, like to try to open it, and then the enclosure. I don't know. You can 3D print another one if we break it, but the license side is gonna be fine. Just disconnect it, and then we see. Try to open it, and then we see what has inside, and if we have the cable to connect to it.
Okay,
and we try it, because probably the thing, I don't know, but normally what happens is that it's just the USB that fails.
yeah.
And then you can directly connect to it. Probably
Okay.
you have to just back up the information somewhere else, and that's it. But at least you can.
Yeah.
So try to open it and we'll see.
Okay.
And then we ask Guillaume if he has
Okay,
the cable.
perfect. Thank you.
do you think about microelectronics?
What?
Microelectronics.
What does microelectronics stand for?
No, I was what I was looking at was this thing called smart packaging.
Sorry, what?
Smart packaging. In this case, it's more like a dispenser, or you have like those packets, for example, to absorb oxygen or CO2, or like these different gases, or to emit. But I've seen on those videos about smart packaging that you can have like a microelectronic thing that does that dispensing or scavenging by itself.
I don't know what that means. Sorry.
I know it.
It's not. I mean, do you have like references or something for it to check?
I mean, I have the scientific articles, a few YouTube videos,
And
but it's something I'm still trying to understand too.
okay. Well, I think the first step is that then to
Yeah.
Hello.
Mira lo que me acaban de... Hay un grupo que son bastante nazis, en plan. Son muy nazis. Es una mierda lo que pensaban las barras, tío, no sé por qué. Okay, guys. So it's muted. No.
Recording.
Recording. Okay, that's good.
Okay.
So steppers, the other type of motors. Actually, there are in the family of motors. We can define it in three big families. We have standard DC motors. We have stepper motors. We have actually four families. Brushless DC motors, BLDC motors, and we have also servo motors. But right now, we have seen DC motors, let's focus on stepper motors. That are the most common ones and the ones that you will mostly use. So, no queda muy bien. So, what a stepper does, anybody? What's the difference between a DC motor and a stepper motor? Exactly. So the main difference is a DC motor is supposed to rotate continuously, and we have control over the maximum, the revolution that we are rotating, and we control the revolutions by varying the voltage. The DC motors usually have a working revolutions rate, so they have a range. The minimum working voltage, for example, for a, let's say, a RS400 class, that is a small DC motor, is between 5,000 RPM and usually runs at 3 volts to 20,000 RPM at 12 volts. You can run them at higher voltage, yes, for a few seconds. Why? Because motors are rated for the heat dissipation. Actually, all the motors, brushless, DC, steppers, servo motors, have a working voltage based on the heat dissipation. Higher voltage means higher current, means more energy translated into movement and also into heat. The casing of the motor can dissipate more or less heat without getting the temperature higher and higher and higher. If you excess the working voltage, what they will do is they cannot dissipate the heat as fast, and by so they burn. How they burn? What is it? What they say in the chat? I don't see the chat. Why? Blink. Huh?
So there's no stall?
The DC motor, they also stall, yes. So the coil that is making the cable that is making the coil has a little sleeve of resin, really thin, around the coil, around the cable. So actually, when we look close at the section of a cable, we have one cable, one cable, one cable, and they are all separated by the resin cover. So what happens if you exceed the temperature that the motor designed for? What happens is the coils get really hot, 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 and hot. What happens? This resin melts. basically burns and disappears. What happened with two of these resins melt and disappears? We have a short circuit between these two cables. If we have all the cables wrap around, let's say all the coil, what happens is instead of having the current going through making all the lines, it will just really go directly to the end of the coil. That means automatically a short circuit. The motor basically starts on the smoke. What you see the smoke is actually the resin burning out, and finally to the motor failing because it's not making through all the circles in the coil. It's just going through the shortest path. That means motor burn. And usually that looks, if you want to see if a motor is burned, it's quite easy. Is DC motor burn coil. It looks browny. Looks something more like this. Basically, all the cables are black. Because what happened is the resin when it burns turns in a black color. Or might also lead to actually the cable, the main copper cable, breaking up, splitting in half because of the heat dissipation. So let's go a little bit on that is heat management. So actually, even if a DC motor is supposed to run at a maximum voltage of 12 volts, they can afford a few seconds at a higher voltage because if you compensate back, you can then dissipate the heat. So actually, you can always play a little bit with the range of working voltages. It's not the same constant peak voltage, and other one is peak voltage. So actually, the motors are rated to a constant voltage, and depends on the motor, they might take a peak voltage also. That is actually the maximum that it can be able to afford. Stepper motors are the type of motors that actually they don't have a high rotational speed. I think the maximum rotational speed for most of motors is 200 turns per second. So it's quite slow compared to a DC motor. What they do, on the other hand, is they can control the position. So there are motors that are supposed to run a slower rotational speed, and we control the angle. It means we can control if we have rotate. In general, most of the stepper motors, we have a minimum rotation angle of 1.8 degrees. That is, as always, this is a generalistic approach. There are always other type of stepper motors that have higher or bigger angles. But the most common angles for a stepper motor is 1.8, 2.7, and 0.9 degrees, being 1.8 the most common one. So the minimum rotation that we can produce is 1.8. That is theoretically, because we can then reduce that rotations with some small tricks. But let's not go into that. Let's go for the basics for now.
How come all the, like your old microphones is like 0.9, 1.8?
Because of the coils.
How many degrees do you have in a?
Divided by the coils and stepping. So actually, in a simplified way, a stepper motor is two DC motors fighting each other. This is a really simplified approach, but it's the easiest one to understand a stepper motor. So let's say we have a motor A and motor B. If motor A rotates to the right and motor B rotates to the right, what we have? A combined movement, that means we are rotating to the right. If, on the other hand, motor A tries to rotate to the right and motor B tries to rotate to the left, what we have? We are locking in place. Actually, we cannot produce any movement, but we have two motors making force to actually keep the position. You have to think that right now, these two motors are combined. I will draw it in the different colors. Are combined. We have a red motor and a blue motor. They are exactly in the same position, both motors, in the same package. So when motor A rotates to the right And when motor B rotates to the right, we actually rotate clockwise. When they do the opposite, they rotate counterclockwise. And when they actually try to rotate each other, they lock the position in place.
But if you alternate between them, you create a loop.
Sorry?
If you alternate between them, one first and the other one, you create a loop.
You create a loop. Yes, exactly. That's how we move steps. So actually what we do is we first rotate, turn on motor A. We start in this position. Motor A rotates, initiates the movement, and we rotate 1.8 degrees. And then what we do is we switch on motor B to keep the position. Actually, that's one step. We just switch half of one coil to move, and then we switch everything to lock the position in place. Actually, that's how we control the movements and how we do every step, by disconnecting some coils and connecting some coils. We can have what is called microstepping, that is have a fight between constantly, but that is done by software, by natively hardware-wise. The motors basically is turning on a coil, off on the other one. This is a simplified and actually quite indicative sketch on actually how a motor works. This, for example, we have the coils. This coil is connected to this coil, is connected to this coil, is connected to this coil, and this will be motor A. Meanwhile, for example, let's draw in green. We have motor B. Actually, there are not motors in a stepper. This is called coils, line of coil A and line of coil B. But basically, it's taking the concept of a DC motor and just put two motors together, alternating each coil. Motor A, motor B, A, B, A, B, A, B. And by switching one of them, what we produce is the rotation of this guy. What is the step size? And the angle size of rotation is again 1.8. Why? Because it's the subdivision of magnets that we have. In this case, you will say, okay, this is not 360 divided by 1, 2, 3, 4, 5, 6, 7, 8. Actually, this is not a 1.8 degree rotation motor, because in this case, we have only 8 magnets. Dividing 360 between 8 magnets, actually rotation of this guy is 45 divided by another 8, that is the one, is 5 degrees, because we need to divide the coils per the magnets, amount of magnets, and we total is the amount of steps that we have. A normal DC motor, a normal stepper motor, what it looks like is like this. These are all the lines of polarity of the internal magnet. In a stepper motor, the coils are fixed, and we have the magnet rotating inside, like this. And these are actually the angle of rotation that we have. So actually, the subdivision of this is we have 200 magnets distributed radially until 360 degrees. That is the resolution of our motor.
It's the closest magnet to the center of the coil, but the coil is it's like 6, 7 magnets. It's the closest magnet to the center of the coil, which gets attracted, or?
Yeah, actually, what we do is, that's one of the reasons why the stepper motors have a really low power to weight ratio, is in this case, we are alternating this guy, and this guy, and this guy. So actually, it's 3 per coil. We don't align one magnet per coil because it will be too difficult to manufacture, like to make a lot of coils for each magnet. So we simplify by making the average between the maximum amount of magnets per coil. Actually, that's how like more expensive steppers are done. They have more coils, but more coils also means more difficult to wire and increases the manufacturing price. It's like cheaper motors have less coils because they are easy to wrap around, like long cable, long sleeve. Actually, how you manufacture coils and motors is quite interesting. It's a machine that rotates really high speed, really long sleeve of cables, and it's like a switch watch. It's quite interesting. So what happened with the steppers? Most of the time, when we are rotating, we are just using one of the coils. As we see here, let's clear this drawing. As we see here, we are only using one of the coils. Actually, you see that we only have two LED LEDs on. It's also simplifying. It's actually if we could stop, we are making a cross pattern. We switch on the cross and we just flip the cross in this case. What happens? We are using a motor, but only half of it is actually creating the movement. So actually that's why in general stepper motors, they are heavy. So if you compare the, let's say, maximum torque of a DC motor and maximum torque of a stepper motors, the stepper motors have double the weight for the same torque because we are only using half of it most of the time. But it's the easiest way that we have to control steps and movements.
When if you go back to the car, like the inside view of the
yeah. This one?
Yeah, technically, I would call it a wheel. Like what's inside of it that's moving with the little steps. Is there a magnet in the middle that's moving?
Magnet is moving.
Is that how is it rotating? Because it has an axis.
Yes, so it has an axis. Let's say this is the axis. This is the side view. We have two bearings. It's basically a metal shaft, and this is a complex magnet that is actually a lot of magnets in just one ring. And basically what this is doing is rotating.
Some terminology in motors. I don't know if you mentioned it, but the thing that is static in the motor is called a stator. And stator. And the thing that the part is rotating is the rotor. Okay, and in the stepper motors, the stator is the outer part and is the one that we actuate in, and the rotor is the inner part. And is the one that has the magnetic, the ferromagnetic elements that we don't control, that they just align themselves to the different poles on the stator. You'll see that this changes. For instance, in brushless is different.
Yeah, so that's where most of the motors in general are what we call in-runners. In-runners. So the part that rotates is inside. So DC motors in general, stepper motors, I haven't seen that outrunner yet. The rotating part is inside. Other type of motors, they are called outrunners. So, for example, that's a different. An in-runner, the magnets are inside and rotate inside. That has a lot of benefits. First, everything is closed and it's protected. We can grab from the outside without any problem because it's fixed. In outrunner is the opposite. The magnets are on the bigger side, on the outer side, and the inner part is rotating. So that creates a lot of difficulties on installation. First, imagine that this is rotating at really high speed. If you touch this, you get hurt. It's dangerous because we have a high speed rotation cylinder. Second, is more difficult to hold the motor in place. We need to do it in the shaft, aligned in the shaft. Let's say like this one. We need to hold it from the back because all this metal casing is rotating. What will be the benefits of one among each other? Actually, as this is outside and we have a lot of mass, we have more inertia, we will have more torque. But we lose a lot of benefits. It's difficult to hold. Usually it's bigger and more dangerous. In the in-runners, in general, are safer, easier to use, and protected on the environment of dust, water, whatever, etc. And usually in runners are more prone to be for high speed because we can rotate really fast because we have less inertia, and outrunners tend to rotate at slower speed than in runners. So outrunners in general are lower spectrum of RPMs, in runners are higher spectrum of RPMs. But that is not only defined by the casing, but also on the type of motor. If it's a DC motor, if it's a stepper motor, if it's a reverse motor, it's a servo motor. In runner are always weight, because that depends on the type of motor. The electric cars that have one motor, they are in runner, and then with some years, they translate the movement. Some electric cars, or for example, the scooter wheels that you can rent on the street, or the electric bicycles, actually all of them they are outrunner. Why? The ones that are on the wheels. We use the wheel as the holding part. So actually the outer part of the wheel is the outrunner part. Think about the electric bicycles. Where do you hold your motor? On the center. We hold in this part. What is the part that rotates? Where the tire is. Actually, scooter motors are outrunners. So if the electric motor is integrating in the final wheel, usually tends to be an outrunner. If the transmission is moved through some gears, belts, etc., usually tends to be an in-runner because you don't want to have the other casing rotating.
So when you need more parts in the system, you use more.
Usually outrunner. For example, why they use in this electric scooters is because we have a small motor that is packed. We want to have more inertia as possible. It's easy to rotate a small wheel, but difficult to make force with a small wheel. Actually, we put the pieces out to have more inertia. Okay, so stepper motors, how we control them? How we control a stepper motor? How we control a DC motor? In both directions.
What is the last circuit that we saw?
An H-reach can control a motor rotating back and forth. What happens if we have two? A double H-reach, that is just the example that we saw. And actually, the H-reaches is just a peak or the little device that controls them. In general, for stepper motors, we have something that is called a step stick that is already pre-packed, but we could do it with any double H-bridge. A step stick stepper. So they are already packed and, let's say, predefined to be used with a stepper. If we look at the step pin out, it's the same. Basically it's a double H-reach, just packed in a small package and already predefined to be used with a stepper motor. So we have both coils of the stepper, coil 2, and we have A and B of the same coil, and coil 1, A and B of the same coil. Then we have the power in for the motor, the B mod, that is the main power supply, that this one, in this case, is rated from 8 to 35 volts. And we have the logic control. What happened? What's the main difference between a step stick and a double H-bridge? What will be the difference? Any clue? The logic, exactly. So a double H-bridge, a standard microcontroller of H-bridge, we directly control and switch on the gates by sending the logic that we have code the logic. We code the logic and how they open and close the transistors. Meanwhile, in a step stick, we don't control how the transistor opens. We just tell, okay, I want to move one step. And this guy manages everything. How fast do both gates need to open and close? So what they do is they input a layer of abstraction on top of us, so we don't need to work on the basics on how fast we open and close the doors. What we do is just say, okay, I want to move one step to the right direction or one step to the left direction. So actually they simplify a lot on the coding part because we don't need to know how fast we switch on and off.
What happens with the printer model, right?
Exactly.
What, sorry?
For the 3D printers, like 3D printers, laser cutters, like almost all the machinery, we have a layer construction done on the hardware side by these step sticks, or also called stepper motor drivers. That's the long name. Step stick is the name we use for the small stepper motor drivers, but these guys, these ones are for the small motors, but if you look for a stepper motor driver, you can see right now the definition. We can have the small one, or we can have the same one, the big one, that it just does exactly the same. Oh, really small image. This guy. Hey.
What we would use the machine week, design week, was a stepper step stick.
Step stick. So actually this is exactly the same. What happened and why it's so huge and big? What will be the reason why it's huge and big of the same? It does exactly the same. More current, basically heat dissipation. Basically these guys, they have embedded like big, all the casing is a big heat sink to dissipate higher currents and higher voltages. So for example, this one is saying here, the peak current of this guy, of exactly this model, is 4.2 volts, 4.2 amperes. 4.2 amperes is a huge motor already. Have in mind that, for example, the laser cutter motors, the ones that we have on the big, on the medium laser cutter red one, these ones are consuming around 2 amperes at the maximum. Probably the CNC one, I'm not completely sure, but they will run around 3-4 amperes, not more than 5. The big CNC. So actually that means we are talking about huge motors already. So these guys,
Maybe
chat questions. Okay, I can read it here. Yeah. No. So here actually what we can see is we have poles, that is steps. We just send a pulse for one step. It's like high. It's between high and low will be one step. High, low, twice will be 2 steps. We have the direction. We just pull it high to rotate clockwise, low to rotate counterclockwise. And we have enable or disable. It means switch on and off the whole device. Why? If you are not moving the motor, you don't need to run electricity through it. Basically, you are just wasting electricity and producing heat in a useless way. So what you can do is switch it off temporarily. Then we have the power supply for the motor, and coil A and coil B. And you can see here that we have a table that is called pulse per revolution table. This is something that is embedded into the stepper drivers controllers, and it's called microstepping. Microstepping is slightly more difficult to explain, but if we can simplify it a little bit, is stepper driver is divided more or less into 1.8 degrees until we get a full rotation. That means 200 steps. We can produce 200 steps to have one rotation. And we do this rotation by having the coils, let's say these are the coils, more or less, aligned with the magnets, no? This is the minimum subdivision we have. And this is having on and off lock in place. What happens if what you do is you stay in the middle position? How do you do that? By having two motors fighting each other all the time at really fast speed. So it's the same as if you have a ball and you are launching it between both hands. What is the position of the ball? The possible one is on my right hand or my left hand, no? What happens if I'm launching the ball all the time? Am I doing it really fast? The ball is in the middle. This is called software microstepping. So basically, we have both motors fighting each other. So actually, we never reach a final position. And this is called subdivision of the coils. And we do this by having both on really, really fast. And the good point of this is we can do it incredibly small. So we can actually subdivide this space by half, by 1/4, by 16. We will have to divide a lot. Actually, we can augment a lot of subdivision that we have onto the coils. So that's how, for example, a 1-degree motor can produce like 0.1 millimeter movements in a stepper, in a 3D printer, in a laser cutter, in a CNC. This actually, we just subdivide the hardware constraints by software. We are keeping middle positions. What happens when you microstep? Actually, you have a power loss of torque. The more you microstep, the more torque you can use of the motor, because you are constantly having both motors in the same state. So usually, if you want to have the full torque of the motor, you don't microstep. If you want to look it for accuracy, you microstep, but you have to know that you will lose torque. The more you microstep, you lose torque. And it's actually slightly exponential. You have curves of this for each motor.
Does it mean that we have torque instability, like when we're beating the coils or when we get just in the coil?
You have more stability when you're in the coil than when you're not in the coil. So actually, you are in an unstable position that you need to be constantly held by both coils, and you need to actually do the control. The good point is the stepper drivers, they do this for you. And they have the pulse per revolution tables. So actually, they are telling you how many revolutions you will have for your motor. For example, in the first one, this stepper driver controller will, no matter what, have 400 pulse per revolution. That means it's actually microstepping by half your motor if you have a 200 revolutions motor. The next one will be 800. So actually 1/4 subdivision of your motor. And you can actually choose to have more or less definition. This is slightly confusing, this part. Yeah. So in general, we try to use, what we do is, if only you are looking for accuracy, a lot of accuracy, you don't microstep your stepper motor, you run them in a standard way. But think that in case that you want to have a smaller movements, instead of 1.8 degrees, you can always microstep to 0.8, to 0.9, sorry. Or you can microstep to 0.45 degrees. So you can produce smaller movements. And this, you do it by the switches that you have on the stepper drivers.
Puedes abrir la documentación de la RepRap, de Stepsticks.
Sí, de RepRap.
Sí.
What is the limit of subdivisions that you can do for those for the microstepping?
Depends on the stepper driver that you use.
So how many switches it has?
So, for example, have you realized that downstairs some printers they make a lot of noise and some printers they don't make almost noise, no? Yes? Why? When you make a full step, you're moving a lot. If you do a small step, you just move a little bit. Actually, that's a motor rotating, creating vibrations. If you reduce a lot these steps, you reduce a lot the vibrations. So actually, for example, the new screws that we have has 256 microstepping. Meanwhile, the standard printers have 164. That is 64. So actually, the newer Prusa has 4 times more subdivision. That means it's creating 4 times, or not 4 times less noise, but half of the noise. Because each step is smaller, by so produces less vibration, by so produces less noise.
What about the definition? Is the difference between
Also augments the definition. The augmented microstepping is not only for the noise, it's a side effect, but the look is actually more definition. Step rates.
Stepper motor.
Microstepping.
Este? Abajo. Just a comment, but all these things about, this project, RepRap? Yeah. For those that don't know about it, is a project that I started some years ago with the idea of making machines that can replicate themselves, and that mostly for 3D printers, that basically are machines that can fabricate parts of other machines, like the ones that we have downstairs. There's a 3D printer built with some components that you have to buy, like steppers, things like this, and also other components that you fabricate with the same family of machines. There's a huge family of machines that are all open design, super nice documentation as well. And all of these things, they have also very good documentation about stepper motors, not only about this thing of microstepping. They talk about what is a NEMA motor, what is microstepping, what is a step stick, what is how to design for them, etc. So have a read into it. It's an open, very, very powerful wiki. So I just encourage you to have a look about all these concepts if they are not clear. They have very good pages also about step sticks. For instance, if you want to understand how to regulate them, what the heat dissipation implies, what type of step sticks to pick, etc. So have a look about. Okay.
So steppers in general are named to the convention of size. That is the NEMA convention that actually here in this, I didn't know where the name come from, and it says here, National Electrical Manufacturer Association, NEMA, that is based on the size. We have NEMA 8, NEMA 11, NEMA 14, NEMA 17, NEMA 23. They have different dimensions. And for example, this is actually where we buy the motors. They have a really good data sheets of the motors. Stepper online. For example, this is a NEMA 17 and this is a NEMA 17. This is a NEMA 17 and this is a NEMA 17. What will be the difference? The NEMA 17 actually is the distance between the holes to attach them. And in the same, let's say, size, we have different depth. More depth will be more size of coils, more size of magnets, more torque under the same size on the XY plane. Let's go, for example, to this one that is a quite standard motor. Quite standard NEMA. It's almost the standard for 3D printers, this one. So this one, they say, for example, the step angle is 1.8 degrees, the native step angle. The holding torque is 15.8 newtons per centimeter. It has a rated current of phase of 0.31 amps. This is the power consumption of the motor at a maximum holding torque. The working voltage is 12 volts. The phase resistance is etc., etc. They also state the dimensions, the cabling, and if we go to the data sheet, in general, they have a holding torque curve. In this case, it don't have. Let's look. I know a motor, so that will have it. Yeah, torque curve. So actually, stepper motors, they have a particularity. The faster you rotate, the less torque you have. Why? Have in mind how a stepper motor, how a DC motor works. If you have all the time the coil in one fixed position, you are rotating at higher speed until the motor maximum theoretical speed that is based on the bearings, etc. what happened with a stepper motor? It's not keeping the coil constantly on. It's actually having it switching it on and off or really fast. So actually that produces a little bit of time that the motor is off. So actually faster you rotate, less torque you have on a stepper motor. A stepper motor works the best at really low speeds, like doing small steps. When you rotate a stepper motor really fast, you lose torque. And actually this is the torque curve of, for example, this stepper motor. So you have 180 newton cent per centimeter at 5, well, actually this is around like 100 RPM. That is 1 rotations per second, more or less. The faster you rotate, less torque you have. And you can even lose half of the power of the stepper based on your speed. So it's important to know this kind of tables and how to dimension a motor. Any questions about steppers? Apart of a lot, they are complex to in the how they work, but actually they are really simple thanks to the stepper drivers. They make it so simple to use them in general.
When we talked about the double H bridge and the step stick, we said that the step stick has a layer of abstraction that allows us to use it without having to
have the control the time that we need each coil on and off.
So it's about the coil, it's not about the timing of how the actual motor moves. So
Exactly.
If I have an object that I want to move, I don't know, say whatever, at 10 degrees every day.
You will need to decode what is actually moving 10 degrees.
Mm-hmm.
So you need how many movements? 10 degrees, let's simplify, 18 degrees.
Okay.
You will need 10 steps. What is moving 10 steps? Actually changing twice the direction of the coil. So actually you will need to have each coil turn on and off 20 times, each one in an opposite direction. So actually you need to decode that. What is easier? To actually have a code that is like switching the logic pin 10 times high, low, high, low, high, low, high, low, high, low, high, low, and the motor logic pin doing the opposite, and the other 4 pins like the 4A and 3A doing exactly the opposite. It's a balancing between the pins all the time, or just saying like switch on and off the one pin 10 times. So actually the layer of abstraction for using stepper motors helps a lot, simplifies the process. Yes?
I was just wondering if you can give us 2 examples of each, like in everyday life.
Of a stepper motor?
A stepper motor. So there's the electric wheel that you were saying.
Application, like everything that you need control for a position. Like a DC motor you cannot control how much it moves, but just the speed.
Okay. Yeah.
But a DC motor, for example, usually the slowest ones have like 3 rotations per second, but you don't control, how much in angles you are rotating. So, for example, you can have a motor that rotates slowly, let's say a Roomba, like the cleaning bots.
Yeah.
They need to know how much they have moved. They can do it by knowing the speed and the time they have spent, or actually knowing the amount of rotations they have done with the wheels. There are 2 different ways. So actually depends on how accurate you want to be. Machines, for example, as a 3D printer CNC, you want to really know how much you're moving. You don't want to have an estimation on time. So that depends the application that you're running. For example, electric bicycle, they are not DC motors, but simplifying this. Before they were DC motors, now they are not DC motors. But electric bicycle, you don't need to know that you're rotating 100 meters. What you need to know is actually rotate at that speed. That is easier. So you don't need to have a stepper control. So in that case, you go for a DC motor.
There is a way to control a stepper as a DC motor. Like I'm thinking, for example, of the machines we made. Like we use stepper motors, but it would have been better to have DC motors There is no way to control both cars to behave like a DC motor.
Theoretically, yes. I never tried. Like if you use a H bridge, a double H bridge, you probably could use it as a double DC.
You would just connect the cars like if it were one motor.
Yeah, never tried.
So you're just moving in the same direction if you do that?
Yeah,
You never,
in that case,
you never tried it.
exactly. You will have both working in the same one, so it will be like, it will behave the same as a DC motor, but in that case, you will choose a DC motor.
Yeah. Okay.
Then we have, so actually, this is how you drive them with waves, and this is the stepper stick is what it does. Here we have a video that's explaining a little bit and the diagrams that we just went. In a stepper motor, just to summarize, we have two types of stepper motors. We have unipolar and bipolar. Unipolar, before they were popular, now not that much. We tend to use bipolar. It's almost the same, but imagine that you are taking another connection in the middle one. So actually it's having like motor A, motor B, motor C, and motor D. It's like having 4 DC motors in one. Those ones are not widely used right now because actually you are only using 1/4 of the motor, 1/4 of the total coils at a time. So in general, what you need to care is if you have at some point a unipolar motor, you can always use it as bipolar. How? By, you can make a little modification, sorry, let's clear everything, that is not using this cable. Using these ones and these ones. It will be the same schema as a bipolar. It's a motor that is a stepper motor. It has 6 cables. If you just use 4 of them, 2 of the same coil and 2 of the same coil, you actually just transform it down bipolar motor. But bipolar motor cannot be transformed into unipolar. But unipolar motors, they are more prone to be used in general with double H bridges, and bipolars, they are tend to use with step sticks or stepper motor drivers. Before, they were more popular because stepper motor drivers were really expensive. But nowadays, they are so cheap, like really so cheap, that makes almost no sense to use still unipolar motors. For example, if you buy an Arduino kit, usually comes with a unipolar because a little bit of saving, little bit of money.
Can you put an image? You've seen them. They normally look like a blue.
Vale, Arduino. These guys, they usually come with your Arduino kits. They are unipolar motors, but you can use them as bipolar. Just by actually this guy here. You open this cover and you just cut with a cutter knife the cable. Finished. Modification.
Just one question.
One of the cables.
Open question. If you scroll up.
Wait. Actually, what is this? No, actually, this is a double H bridge. They come together usually with a double H bridge, and you have like the 4 pins to actually activate them.
And
So this one's so little that you have a lot of heat.
No, doesn't drive this.
Why? So you see the shaft is not on the center. Why is that? You see the shaft in the first one? It's not in the center. Why?
Yes, exactly. This motor is so small that has almost no power that have a small reduction gear to
increase torque.
Increase torque.
A gear, well, like you can use gears to with this something that is rotating at a certain speed. You can reduce the speed or increase the speed, and If you increase the speed, you reduce torque. If you reduce the speed, you increase torque. Okay.
And actually, the stepper reduction gears are quite popular because usually with the steppers, you don't want to run at a really high speed. What you want to have is accuracy and torque. So actually, putting a stepper motor with a reduction gearbox like doubles the amount of torque in general at minimum, and you don't lose that much speed, and you actually have another consequence that you have holding torque. A motor, when it's off, it's easy to rotate. A stepper, depends on the size, can lead to. If you have a gearbox, you cannot rotate it. So for example, the big CNC, I don't know if I try to push it when it's off, it's almost impossible to rotate in place. Why? Because with the motor is not directly attached. We have a gearbox in the middle that actually is multiplying the amount of torque. So it's widely used to have two applications. First, when the motor is off, to lock the mechanism in place, and second, to augment the torque.
Even if the is off, it's blocking the.
Yeah, and down we have a lot of, actually we have a gearbox that is 1 to 23. It reduces 23 times the, actually augments 23 times the torque. It's impossible to move by hand, even with a big wrench. And then we have, for example, a servo. These ones are you are more used to, no? A servo.
You use them for the ice cream there, no?
Okay, you have used them, but in another color. Come on. These guys. These guys, actually, they're funny. They are called servo in amateur hobbies, but they are not a servo motor. These are wrong, the kind of definition is slightly confusing. Let's simplify. What a servo is a device that rotates in general, but it's constrained on the movement. We can control the position, but we can only rotate usually in general from 0 to 180 degrees. So we can only do half turn. How these guys work, but let's go first on how we control them.
And why do we have the one that does 360?
There are some of them that they can do, but in general, I'm taking about 80% of the market. They rotate 0 to 180. Then we have like 0, 30, 0, 60, 0, 90, 0, 100, 0, 170, 0, 270. But in general, they never finish the circle.
I think the question is, why do they exist?
Why did they exist? For example, I don't know, your coffee maker that pushes your coffee cup out. You just need a small movement of a lever.
So it's cheaper actually.
It's a really easy way to produce a small movement that's constrained. For example, let's say we have the blinders. To close a blinder like this, you need just a small rotational movement. You can produce it with a servo motor, as little servo.
Windshield.
Sorry?
Windshield wipers.
No, they are not like that. But it could be an application. If a servo motor, you have a big one and you connect it just like that, could be a windshield wiper. For example, yeah, could be exactly like that one. So these guys, in general, we control PWM most of the time. The good point is we do it transparently. So full cycle PWM will be maximum angle, minimum cycle PWM will be 0 angle. Middle cycle PWM will be half angle. In Arduino, we have libraries that they do is we just say, okay, I want to rotate 30 degrees. When you type servo angle 30 degrees, what the library is doing behind is setting up the PWM at 30% cycle. But actually, it's quite interesting how these guys work. It's loading, it's not loading. Okay. So this is says 1 millisecond between activations is half angle, 1.5 is 90 degrees, 2 milliseconds is 180 degrees. This is just the PWM. But these guys are quite amazing how they work inside, because they are not, I just looked for it before, here. Is the silliest device ever. They have a layer of abstraction inside, and all the servos inside the box, they have an IC to control them. So we have a pre-programmed microcontroller that is managing everything for us. But basically what they have is a DC motor. When you say, okay, DC motor, but we want to control accurately, like it makes no sense. Wait, we have a DC motor with a high gearbox reduction. So actually, if the motor is supposed to rotate at 1000 RPM, we reduce it to 2 RPM. This gearbox, that's why we have so many gears, they reduce a lot the speed of rotation. By reducing a lot the speed of rotation, what they increase? The torque. Actually, we lose the speed that we don't care, and we gain a lot of torque. So actually, it's a really win-win. We can produce a lot of torque with a really small motor. And okay, how we know how much we have moved? Because in the final year, we have a potentiometer. What a potentiometer does? Measures from one direction to another angle, and they measure the resistance. So actually, this guy, what we do is, okay, PWM 0. It means go to the minimum position. This IC is gonna activate this little H bridge to be able to change the rotation of the motor, and it's gonna start moving. It's at the same time measuring this sensor to know the total amount of movement. In the moment it has reached that position, it stops. So actually, we have already a really small device that is really smart, because it has an IC activating and reading the sensor at the same time. And it's actuating based on the readings of the potentiometer. Yeah. Okay. We say go to 30 degrees. The IC is gonna make the motor rotate, for example, clockwise, because before it was in 60 degrees. Okay? So it's gonna make it rotate. The gearbox is gonna start rotating. The lever is gonna start rotating in one direction. And by so, the potentiometer is gonna change the value of the resistance, because the potentiometer is attached to the main shaft. We read the value, and this guy will have a table that says, okay, resistance 0 equals 0 degrees. Resistance, I don't know, 10 ohms equals 180 degrees. So actually, it's reading the sensor at the same time that is actuating.
How do you read the potentiometer?
It's an analog.
Voltage divider? Into what type of pin? Exactly.
What did you say? Sorry.
How do you read a potentiometer?
Yeah, well, what's the answer? That's the question.
I don't know. So it's just potentiometer is a variable resistor. You remember the circuit of a voltage divider? So voltage divider, potentiometer is one of the resistors, and you put that into an analog pin of your microcontroller, and you have the reading of the potentiometer.
So actually, this small board that is already packed inside here is managing everything. We just need to tell how many degrees we want to move. We don't tell the degrees, we tell the degrees that Arduino translates into a PWM. This guy reads a PWM and knows how many degrees he needs to move.
Just one thing here is that one thing that here that might be confusing is that the PWM that we're sending is not actually directly talking to the motor. So it's not as if what we were talking earlier, that we are opening or closing a MOSFET and that is changing how much we're feeding the motor itself. Is a communication protocol encoded into PWM. So you send PWM, you say angle PWM, and then the other one gets PWM and understands that because it has another ADC inside, gets PWM, and then gets converts that into instructions for the motor. Yeah.
So it's like the lazy motor. You don't want to
No, I mean, in this case, it's more like what we are doing is not sending the PWM as an instruction to the motor. That is being managed by the microcontroller in the servo, but the PWM is just like the radio frequencies that we send FM or AM. You remember FM? Like the way that we can modulate information into a channel with pulse modulation is the same, and that is what we're using for communicating between both microcontrollers. Okay.
your son's gonna shut off in 45 seconds.
What?
Or the two.
So actually, this kind of devices is what we call closed loop control. That is quite important. For example, a DC motor, we just put voltage and it moves. We don't know how fast it's moving. We can estimate it based on the voltage and the data sheet. In this case, we have actually a sensor in the device. The sensor is keeping the position where it needs to be. If you manually, the angle is like this, and you manually move it 10 degrees, when you release it, it will actually move again to the same position. So actually it's a closed system because it's actuating and reading to check that the system is in the correct position. And it's quite important. Why we want to have closed loop control is to have repeatability, to know that we actually move the amount of movement, we produce the amount of movement that we want to produce, and we do things in a way controlled way. This, I said before that these servos are not what we call industrial servo motors, but they work in the same concept. They have the same concept, but completely different ways of how to do it in the hardware side. Industrial servo motor does the same, but at really, really high cost with really high end performance and really good materials. In general, for example, these servo motors, a really good one costs 30 euros. An industrial one can cost 1,000 euros. It's a really jumping price. For example, robotic arms, they use industrial servo motors, or like factory chain, they use servo motors because they want to produce the same movement again and again, and they don't want to miss even 1 millimeter. That with a stepper motor, for example, if something, a little bit of debris goes into the rail system, the stepper might lose 1 millimeter of movement. That will be a cost endlessly of a production chain. If they are manufacturing iPhones and the chain stops working badly for 1 hour, you lose that money. So actually you have motors that can have what is called closed loop control, that is a servo motor, industrial servo motor. Let's not get too crazy into that because
we still have some more stuff to talk about.
Yes. No, it's not that many actually. It's just LEDs and EL wires.
Yeah, it's not that much.
LEDs, actually, I don't know. It's a little lamp. That's it.
It's very simple. So LEDs, well, you already know about them, but there's some particularities about them. Diode, they're LEDs, light emitting diode. Diode means that it only works on one direction. There's a way to distinguish them, and you have them in the fantastic chipset. If you go up, no, if you go up, Edu, more into the MOSFET area. More, MOSFET.
Sorry.
The Japanese. More. More? Up there? Yeah. What's that?
Here?
More.
Lower.
Is in this.
Ah, okay.
So there you have long leg is the positive, which is the anode. Shorter leg is the negative, which is the cathode. You have also marked in the SMD LEDs where is the cathode, which is the green side, and that is corresponds to the light, the bar, let's say on the symbol. Okay, current flows from anode to cathode. Okay, from positive to negative. That's the only thing that you have to take into account for LEDs in terms of how to orient them. Some things also is that if you go into an LED, you want to purchase one, you have to see how much current do they support. And by that, you have to adapt your current limiting resistor. So the normal resistor circuit, probably should start the screen now, right? Okay. If you go into LEDs, yeah, parts. Okay.
Vale, por ejemplo, vamos entre el red y el green. Así lo vemos.
Okay, so RGB. Okay, so the amount of current that you can pass through an LED, in this case.
Okay, really good.
And the supply field.
Sí. Han cambiado más de link de.
Y lo hacen redirecto.
Verde, sí.
Oh yeah, those are deprecated.
Okay.
Okay, so you see the green line that distinguishes the negative side or the cathode. If you don't see it, a plain side, you just have to like move a little bit and it's like embedded in the side of the glass. And then if you scroll down, you see the maximum amount, the direct voltage and the maximum current that they withhold. Okay. It means that, for instance, if you are using 5 volts in your logic, in your microcontroller, and you want to use this type of LED, you have to put a current limiting resistor. And for that, you have to make the numbers with Ohm law, which is super simple numbers, but that will allow you to calculate the resistor that you have to put. Okay. I encourage you not to do that. To do it by hand is I think it's better. More things about LEDs. Exactly, LED resistor calculator, and that's it.
So actually, for this one, you say that this is 2.1 and 10 milliamps of power consumption at full blast. So you put supply voltage, that in this case, let's say we work at 5. Voltage across the LED, 2.1, and consumption of the LED. In this case, we only have one. Will give us, we need a 290 ohms resistor. If you don't have a 290 ohms, if you use one that is above, you will actually bright slightly less, no problem. If you use one that is below, that what happens is the LED is overheating. That might lead to actually the LED burning away. Or have you noticed that sometimes in the street, some like white lights, they are not anymore white, they are kind of yellowish? Actually, that's wrong dimension of the resistor. The LEDs were white, the resistor is slightly pushed lower to actually bright more. That means the LED is heating up a long time, it becomes burn, yellow, until it starts working.
When you say voltage drop, it's the maximum allowed voltage drop
across the LED. Yeah. Yeah, so it's so it means that if you have 5 volts, 2.1s have to be taken by the LED maximum and the rest by the resistor. Yeah.
They also state, for example, millicandelas, that is the bright amount. Obviously, you have some LEDs that are really powerful, and they will have a lot of brighting, but also a lot of current going through them. So actually, if we look for an LED, some of them, they can get crazy, like up to 5 watts of power consumption, like crazy. So actually, in that case, you cannot drive them directly with, for example, your microcontroller pin. These small LEDs, you can usually drive them directly with your microcontroller. Why? If you look at the datasheet of your ATtiny, ESP, they will state what is the maximum amperes going through the microcontroller pin. In general, that's between 10 and 20 milliamps. That is enough to drive one LED, maybe 2. What happens if you have more LEDs, or you have like a really powerful LED? How you can light it up? With a transistor, aka also a MOSFET, you can also drive them.
Puedes ir cerrando pestañas también.
¿Qué?
Que puedes cerrar pestañas también.
Luego cierro.
Okay, couple of things. LEDs, more current, more light, too much current, got burned. They can be addressable. We will see that in a second. And also not only from a single color, but what we call RGB LEDs. So, scroll down.
Little packages are not just for fun. It's because they have different emitting angles.
Exactly.
So each package, for example, the one that you are used to, that is this guy, more or less emits in 120 degrees angle. And you can find them in 3 millimeter, 1 millimeter, and 5 millimeter. Depends on your application.
Or even more.
Well,
20.
Yeah, they are really big ones. Yeah.
Big fat.
Addressable. No?
We'll talk about that in a second. That is the way of calculating the resistance. And here you have RGB LEDs. RGB LEDs are 3 LEDs in one. By that, for that, they have 4 legs, 3 per color, RG, so red, green, and blue. And then common. The common can be the anode or the cathode. And this is important to check. And both circuits are on the right side. There can be common anode or common cathode, meaning that you have, I think there's an image below. Exactly, no, not that one. No, there's no. So if you imagine 3 LEDs, I can draw it. Or no, I can't. How do you draw?
Annotate.
But I can't. I'm not.
So let's say we have 3 LEDs. No.
Yeah, and either they share the positive, and then they control. You control with a microcontroller the negative. At the end, what matters is the difference in voltage across the legs. And that is called, if they share the positive, the anode, they're called common anode, the first type. And if they share the negative, they're called common cathode. Okay? You have to check which one is which so that you know how to wire them. Okay? I think the ones that we have here are common cathode.
I don't remember.
I think we have the one in the right, but check. Okay?
So if it's common anode, then it would be white, and then if it's common cathode, it would be different colors.
No. The colors don't matter. So the important part is how the wiring goes. So can I share the screen and then I share it on. So
there is no difference on what they do, just if you have all the positive legs connected or all the negative legs connected.
Exactly. So it's only, if you imagine them as normal LEDs, so you have this, like that, and then this like that. And this goes to the pin 1 on the microcontroller, the pin 2, and the pin 3. And this goes to ground. And with the resistors in here, okay? Then this is common cathode. because the cathode is shared. If you did the opposite, instead of ground here and the pins here, you do reverse, but keeping the direction the same, then it will be common anode. Okay. Okay, so I do it. Yeah.
Engineer and design, you do the schematic, I do the physical layout.
Okay, so in here, for instance, it would be 5 volts, and then pin 1, pin 2, and pin 3. This is common cathode. This is common anode. Okay.
The resistance, the charge, how do
You can just put one.
Or you can.
common one?
Depends on the.
I would.
Because usually the red, green, and blue, they have different working voltage and different power consumption. That depends a lot on the specific LED. If it's the one that gives that you are the through hole, you need to put individual ones. The ones that are SMD packed all in one, I think they can just put one resistor for all of them. But in that case, you will bright all of them at the same time. Depends. No, actually, no. I was wrong.
Okay, so then these are types of resistors of LEDs that don't have anything inside. They're just the LEDs and that's it. But there's some smarter LEDs that have some extra intelligence that can be what we call addressable. They have not only the possibility to be lit by just giving voltage, but you send them in a strip as you are able to light up an LED in the strip because they know their addresses, and there's a change of communication of data between them. So, basically what they have inside is this normal, it's important that you also remember this model, or that at least sounds familiar, is the common LED type. That is, it has an integrated controller inside that basically is able to know what address of this LED is in the strip and also receive information, and you're able to turn on different colors with different levels and intensities. They normally come in this form. You've already used them, something like this. And they have 3 lines: voltage, ground, and data. And you see that there's a little arrow, these little arrows in there, over here. That is the other way. These little arrows specifying which direction they should be connected. Otherwise, they don't work, okay? And the data is sent from one to the next one. You could, if you wanted, cut the LED strip here in the middle in this black line. So you can have 2 LED strips and they will be exactly the same. So when you cut it, if you cut it in here, this will be number 1, number 2, number 3. And in the previous one, it was number 5 or number whatever. But you can basically cut them and have it in different lengths.
So once you cut it, it kind of resets the one.
Yeah, it only matters the relative position in the strip. Okay. One other thing to just keep in mind, and for this I encourage also to visit this NeoPixel Uber guide, super good, talking about the different connections, how to power them as well, and how to control them. Normally, there's some few things that you have to take into account. For instance, putting a resistor before the data line in the first LED so that you don't burn it, or use a capacitor for certain size depending on how big the LED strip is, as well as some other specificities like the voltage levels for the data and things like this, okay? I think that is also like, I encourage you to read it because it's like a little late, but most things is like, or have a look at it and read also the power requirements. Normally an LED draws more or less like 60 milliamp when it's white, but you don't always have them at 60 milliamp, so it's always like a bit less, and you can estimate something like 20 milliamps on average. considering that some of them will be white, some of them will be red, etc. And this, if you multiplied it by 5 meters and 5 meters times 20 milliamps with, I don't know, 100 or 60, let's say 60 LEDs per meter. So 5 meters times 60 times 0.02, that's already 6 amps. So it's not silly. There's a lot of LEDs in there, so it's important, okay? For that, have a look at this. And also consider that they are not normally going to be powered from the Arduino. They need an external power supply, and that you can interface with as long as they share grounds. Okay, so you can power the LEDs from somewhere else, and then
usually
connect it to a microcontroller. Connect it to a microcontroller. Have the logic be sent to the LEDs, but only share the ground between power and Arduino.
Have in mind that LED stripes is really easy to accumulate a lot of current because you have a really high pixel density. So it's really easy to, with a short strip, to go up to 2 amperes.
Exactly.
So usually think that LEDs are power demanding the moment you start having a lot of them. One is not power demanding, but the moment you have a few, the current goes up really fast. So we have in mind that you will need a separated power supply to power everything.
If you have like only red or blue spectrum lights or spectrum, does it consume the same power, or it's like
no? So each color consumes around 20, more or less. Some colors consume more and some less, but you consider that 60 is the white, which is all colors full on, and then roughly a good estimation is 20 per color.
But if you only want to use a red color forever, this doesn't make any sense. This is if you want to change color. If you just want to power red, you have LEDs in a stripe that are all red, and you just give power to them, and you don't need to pre-program or do anything. You just can power it. You can do it putting directly to the power supply, or you can control it with a MOSFET to turn it on and off. So if you just plan to use one color for the full stripe at once, putting a like intelligent addressable LED is a overkill.
For controlling LEDs, 2 libraries. You can use FastLED, quite nice, and NeoPixel for libraries. One, this is Adafruit maintained. This is another open source one. For controlling LEDs in general, if you just want to do a blink, it's fine. But I also recommend that you use this library called JLED, which is quite a good library for controlling LEDs with non-blocking fashion, which means that when you do a blink, you have to do the delay of the microcontroller and pause the execution of the microcontroller for a certain amount of time. Right? If you want to do a blink for 1 second, on and off, you put a delay. And that blocks the execution. Let's say you are not doing anything else while you are in the delay. That, I think, is a bad approach. And in this other way, you do it in an asynchronous way, which means that you don't block the execution. You just tell the LED I want it to be on and off every second. And in the meantime, I do something else. But you don't stop to do that, okay? And it's not a difficult library to use. You can have a look in here, and I use this, for instance, for the same installation as before, the one with the flashes, but instead of LED, I put the big lights with relays, okay? And that way you don't have a blocking process, and you can control lights with different blinks. This one blinks fast, and this one blinks slower, or this one fades in, and this one blinks fast. And you don't have to program complex things. You just address each of them in a different way, okay? Huh? So, for instance, you can do this thing in the image, or you can do like many other things. But the idea is that you don't block the execution, okay? And that way is useful to do smarter things. We have to having to think about how am I gonna control the timing? I cannot do anything else in the middle, etc. This is a very good library. Exactly, and it's mentioned in here as well. Another thing, L-wire is electroluminescent wire. Edu likes it a lot because he puts it in his bike. Basically, this is quite a nice thing. It makes quite a nice glowing effect. different colors, etc. But they work with AC, and that is not nice because you need an extra piece of equipment that is an inverter. So you need something that creates AC from DC. Normally you put like a pack of batteries, like A or AAA or AA batteries into a piece of electron, a small box that generates DC, AC from the batteries, and then you can light it up.
So these guys, basically what they are doing is a flexible way of lighting. It's a cable and it's really flexible. It doesn't break and all the cable lights up. How they work, they have a plastic sleeve to protect them, so it's waterproof. And they have like electric, I'm drawing on the side. They have a little cable in the inside and a positive, well, actually it's not a positive, it's another metal hole in the outside. And the material between is an electroluminescent material. So actually in the moment we run electricity through the material, it brights up. It's like neon effect. Well, to light it up, we need to change the polarity all the time, so we need AC. So we need a little power inverter that is a little box. The good point is we can disassemble these boxes and just feed it electricity to the box or not. So we basically, these boxes, what we do, clear all drawing. ¿Por qué no se borra?
Yeah, I have 3 questions about this.
So basically, we have the cable, we have a box that we need DC coming in, no? And this produces AC. So basically, we buy these devices and we control is actually the DC current that goes into the power translator. They're really small enough to fit in the sole of your shoes, or you can have them really big to have a lot of meters of EL wire. Depends on the amount of meters that you run. Actually, you know that maybe in Carnival or like drone movies, they use this. Actually, they use a lot in this in the film industry to create these like super fancy dresses. They are super good.
When you work that,
Huh? Buy this. The real one I just buy it in Amazon is super cheap in general.
Or any other electronics.
Yeah, the device that, yeah.
If you don't want to buy in Amazon, you also can go to Brico Geek. Brico Geek. Spanish.
I used this to make a
Spanish shop.
but the problem with the tie, it was like an action shot. This guy was flying, and so I was trying to keep the tie stuck to his custom with this double stick tape we use, but the device was heating the tape and melting it off, so the tie kept flying. So that's why I was wondering if this
What's
will
getting
be-
caught? The cable?
Not the cable, but the small device that.
The device,
Inverter.
the cable is cold, so actually it doesn't burn on
Yeah.
anything. Super.
But the device was getting hot, and I was trying to figure it out.
Oscar, I had a question about the EL wire.
Yeah.
Sorry, Jasmine, did I interrupt you?
No, you know me.
It's kind of hard to hear over here. Would you be able to have, say, like 100-meter stretch of wire like this to light up a whole street and plug it onto the AC, like the mains, 220 volts?
The EC current that these devices need to go is around 10,000 volts difference. So actually, what they work is a really, really high voltage difference, but a really low milliamps. So actually, it's not dangerous. They just give you a little discharge, but that's not dangerous. It's like we are talking about, I think it's micro amps of consumption. Actually, they are efficient. What is not efficient is the inverter, actually, to make the translation from a DC low voltage to a AC super high voltage.
Underground, no? I mean, you can't just say that I want this chunk of the, you know what I mean?
No, it's just a piece of wire connected. It's not addressable or anything. It's just a wire that lights up. Yeah.
Yes. So they are self-lighting cables. They are not lighting cables. They don't produce the light of a light bulb at any point. Lights are around 10 centimeters around, but that depends also on the amount of cables that you have.
Okay. So that's, I'll also encourage you, this is SparkFun guide that I had open. It's, I mean, I think that SparkFun and Adafruit have like fantastic guides for many of these things. Have a look at them and spend time reading because they're really well detailed.
Adafruit has guides on how to make all type of clothing with these cables.
Yeah, it's super cool because you can weave it actually. You can weave it.
To solve the problem that she had, is there like a way to kind of guide that would say like, hey, here's how you kind of have some casing for heatsink so that it doesn't help us.
Well, that depends on the quality of the inverter you have in general.
I
Like,
mean, in the end, I did it like how I do with the heat from the mic packs on the matches, is I just wrapped it in moleskin to like, but anyway.
the ones that you use so far, they never heat up. So that depends also, like they are estimated on total length of wire that they can light up. So maybe you force them, this when they start overheating or the light less. They have less
It
brightness.
was like 12 hours.
Also, that depends.
Normally, if you want to protect them for, let's say, overheating, something like a thermal fuse is at least a very easy way to protect something. You can see in many devices, actually, many of the home appliances that don't work, that you say, all of a sudden it doesn't work. You open them and it's only the thermal fuse that is broken because it's just a fuse that protects with both like temperature and amps. And for that, if you can just get the one that is rated for whatever temperature you want, and that's it. You protect these type of things. Yeah. Super easy one. Nothing super interesting or complex about this. But piezoelectric, instead of generating motion or instead of generating light, we're gonna generate sound, or well, vibration actually, from electricity. And sometimes we can also generate sound with them. Not very complex sound, but more like 12-bit or 8-bit sound from the Game Boys and things like this, but with this type of buzzers. So basically what these things have inside is a ceramic plate in between these two sheets that when they are activated or when they receive voltage difference, they vibrate or they produce a little expansion, let's say. And if we control the voltage in there, they ends up producing a vibration. If we put that on a plate, it's like a buzzer or like a speaker that makes the air around it move, and that is the definition of sound. So with these things, super simple, just to mention, well, they don't require anything super complex, just two wires, and you have a tone function in Arduino. And of course, if you want to drive big things like this, not from the Arduino, but you can also use amplifiers. So again, in SparkFun, there is a very nice tutorial on how to make amplification, which is not an easy thing. We jump from the digital world of electronics into the analog world of electronics, and that is not easy. But basically, as someone was asking earlier in the chat, yes, you can use a transistor to amplify something. And basically, that's what you would use in audio equipment. An amplifier is just a set of transistors. And if you remember in MDEV, we talk about combinational and sequential logic, combinational, and actually in FA Academy as well. So these are just circuits that don't do absolutely anything else, but just amplify or reduce signals, remove noise or things like this. And with that, I think that we should close because it's already quite late. And tomorrow, we'll go a little bit deeper, especially into practical stuff, more about batteries, probably some more stuff about motors, and also debugging. So ideas on how to wire for inputs, outputs, what libraries to use, and debugging on when things go wrong, what to do. Yeah. There's class this afternoon. The global classes, as usual. MDF, I don't know. Sorry. Recording paused.
Any questions online?
Oh, Clement, you look like you're an operator.
It's my nerdy headphones.
I want a Whopper.